Sup, nerds? We got a fun stream today. I have a guest that you hopefully are familiar with. If not, we'll be sure to let him introduce himself. He's one of my personal favorite YouTubers, so I'm actually very, very excited for this. So without further ado, does the button work? It does. Howdy, howdy.
How's it going?
Audio working, everybody? Yeah, Casey's far from a YouTuber, but I've experienced his YouTube a lot, and it's really good stuff.
YouTuber is a high compliment these days. If you see those polls that they ask kids what they want to be when they grow up, and it's like YouTuber.
Yeah, for real.
It's like President of the United States or something. It used to be, right? Now it's YouTuber.
Yeah, it's considered one of the coolest jobs nowadays, which I dig because it wasn't a cool job it actually kind of was when I started, because I started somewhat recently. Yeah, it's still weird. Anyways, how would you introduce yourself to somebody who is trying to figure out who you are and what you do?
So I'm probably older than a lot of YouTubers. Maybe not in the tech scene, I guess. I guess there are some old school people in the tech scene, but I've been programming for a real long time. I think I started in the game industry programming in like 1994 or 5, I guess 1995. And I've been around for a very long time. Most of that time was working on actual game engine technology stuff. I worked at a company called Rad Game Tools, which does a bunch of SDK stuff that's used in games. So one of the things we did was a video codec called Bink that most people see the little logo of come up when they're going to play a game or something. I worked on a character animation software thing that we did, and anyway, that's where I did most stuff that's of any note that I worked on. These days, I actually produce educational materials for people who want to learn more about sort of the kinds of lower level programming, like understanding what the hardware is actually doing and understanding how the software is actually interfacing with it and that sort of stuff, which I think brings us to the stream today, because that is what we're going to talk about.
Very exciting stuff. I'll say the things that you're not going to, which are, I made a video where I talked lightly about CPU architecture stuff and tried my best to give an overview while also not knowing enough about the difference between architectures. And I could have told from my comment section I was pretty wrong. Casey hit me up offering not to roast and tear apart my video, but to help me better understand these things. And I'm not going to say no to that opportunity. As you guys know, there's nothing I love more than being wrong, because it means I get to get better and smarter and better understand these types of things. And I've always considered myself a nerd about architecture. That doesn't mean I'm good at it. It just means that it's something that's always been very interesting to me. Casey, are you familiar with the history of Anand Lashempi from AnandTech?
I'm not really familiar with his history, but I mean, I read that site all the time, especially when he was originally doing it, but also when Ian Cuttress took over as well. It's sad that they don't exist anymore, I guess.
Yeah.
But so I'm not familiar with his history, though.
Yeah, I meant more like that. Sounds like you do know what I was going to reference. Like the fact that after he did the article about the iPhone 5S's 64-bit architecture, that Apple poached him, and he leads the storage chipsets now at Apple and has for 10 years.
I actually didn't know that.
Yeah.
I didn't know that. Okay.
He's the reason they could fit 1 terabyte SSDs in the first line of super thin MacBooks. The MacBook 12-inch had a drive that was good because of him.
I did not know that. Well, good for him.
Yeah, he's
good for Apple.
Always been a hero of mine, and yeah, I'm nerdy about this stuff, but as I said before, it doesn't mean I'm good about it. So I'm very, very excited to learn more. I'm gonna get my tea bag out really quick, then we can get started.
Okay. Well, let me also maybe add something to that. I guess I'll wait till he comes back, but I wanted to add something to the preamble.
Only hit 15 things on the way. Anyways.
Let me add something to that, by the way, because I think this is something that's worth saying. It's really hard to be right about this stuff, because one of the things that I find incredibly frustrating, and it's gotten even more frustrating as I've tried to produce educational materials on this stuff, because I want to go and check things, right? I'm trying to make sure that everything's right. It is incredibly difficult to get hardware people to talk about how the stuff works. They are so secretive about these things, and I'm sure they have good reasons. I know that, patent fights happen in that space, and also like there's huge lead times, so you don't want your competitors knowing what you're building, and there's all this stuff. So I'm sure they have good reasons for like their very secretive culture. But one of the things that I find incredibly frustrating is like it's hard to be right about this stuff. It's not like in the software world where if you want to know, if you're not sure how something works in React JS or something, you could go look at the source if you're qualified to read it, right? You don't have to guess, right? But in hardware, it's really not that way. There aren't fun. You can't look at the source, VLSI or whatever they add. You can't look at the source design for a Zen 4. It's all behind closed doors. You can't even ask about it. They just won't tell you. And so I think it's worth kind of noting that it's understandable why people have misconceptions, and it's understandable why people are wrong, because we don't get the kind of information that we would expect if it were software.
Yeah, I've heard so many stories that touch on that point, but never heard it put so like clearly and concisely. Just little things like I remember how impressed people were when Intel's Arc GPU started to happen, and they were being very public with how they were doing things, and being able to talk to the engineer actually designing the chip was considered this like crazy new ground that hadn't been broken before. Or the story I told earlier about Anand reverse engineering Apple's Cyclone architecture because they didn't put anything out about it, and rather than like just go after him legally trying to get him to hide it all, they decided to hire him because they knew he'd be a good asset for the team. All of these stories seem to touch on this point that you're making of like these hardware companies generally are secretive of these things. And I, as an open source nerd with through and through, like not just with my like software engineering, but I try to be as open as I can be about everything I do. All the tools I use to streamline and orchestrate my content process, they're either open source tools that I've put out there or documented the hell out of how I use. I love sharing how I do these things because the part that's exciting to me isn't the individual pieces, it's what we can do with them. And if more people have an understanding of and access to those pieces, it means we can do more fun stuff. Obviously, hardware has a much higher barrier for entry, but it still, to me, just kind of sucks that it's as hard to break into as it is.
Well, and I also just wish, I don't know, it might just not be possible because of the business realities, like I was saying, but I do wish that I could convince some of the hardware companies to be more open just to the software side. Like, I don't really need to know like how does your floating point multiplier work or something, right? Like, but just what a very simple example. I know multiple people who work at NVIDIA. None of them are allowed to tell me. I'm just literally this. None of them are allowed to tell me where a CUDA core would appear on, say, a 4090 GPU. So on the die, I'm just like, could you tell me which, like, because CUDA core is the separate discussion. We probably won't get into that today because that's it. But it basically it's a floating point multiplier, multiply add, right? Is what a CUDA core is. But I'm like, where is it? Can you tell us where it is? Because people have guessed, but no one really knows. And they're just like, we can't, like, we're not allowed to talk about anything like that. So, even just simple stuff, like I just like to understand the die shot of this thing or the CPU, just so I can understand more what I use every day in my computer. They just won't tell you those things. And paradoxically, you're more likely to get information like that from reverse engineers at another company who have used like photon emission microscopy and stuff and done micro benchmarks and looked at what lights up, and they go, oh, well, we know where the CUDA core would be. Like they'd all be like, here's a cluster here and here's a cluster, right? And so it's kind of funny that way, right? And so yeah, most of the time, like if you want to know something like that, like what's the layout of this core, what you're going by are people's best guesses. Like you mentioned that what NN did with that reverse engineering the piece of hardware, that's very common. If you want to know where a CUDA core likely is on a 4090 today, you are going to be using a die shot that somebody on the internet tried to mark up and is very likely wrong or slightly wrong. That's just how it is.
Yeah, that's so much worse than trying to de-obfuscate JavaScript. God,
it is. Yeah.
Yeah, it's
but
funny.
Anyway.
The only thing I've had even similar in our space, there's a couple companies, and the only one I can really think of is Sony, that do really cool things with software, especially with JavaScript and the React side. Did you know the PlayStation 5's entire operating system is based in React?
Oh, really? That media
Yeah.
crossbar thing?
Yeah, the entire, like, from the home thing to when you press the button and like the bar comes up to the store, everything is a React Native app, and the architecture is actually really, really cool. I know way too much about it from friends there, but if I talk about it beyond what I've said here, I could get them in trouble, so I can't. So now I'm waiting for the jailbreak community to find enough of these things that I can use those sources to more meaningfully talk about it. And it's just, it's such, I hate these things. I just want to nerd out about the details because they're fun.
Me too. Me too. Well, and I guess on that note, so let's talk about the basic CPU architecture stuff that because that's a good segue into it. And again, with the caveat that we're going to do the best we can here, because we simply don't get the kinds of details that we would like. And, you know, it's, why aren't there a bunch of hardware designers coming on the stream to talk to you and to tell you, right? Because they're going to know better than I am. It's like, they just don't. They just don't. And so, you know, we're going to do the best we can here. And I'll try to mention very clearly which sorts of things are conjecture here and how much we really can or can't confirm and so on.
Yeah, very thankful to have you here to share this with us, especially considering that they're not going to come do it.
Yeah, and believe me, I have tried, but they just don't want to. So what I did is I took a look at the video, and I took a couple of screen caps here just to kind of remind me of like what the sort of things were that were discussed. And so one of them was you were kind of talking about this concept of an ALU, which for people who don't know what that is, it was the term arithmetic logic unit. It's existed for a very, very, very long time. You can go way back decades in chip architecture history, and you will see this term used. And it refers to something that does fundamental computations. And, you know, I don't really know the exact history of the term, but the reason that we say arithmetic logic unit, or sometimes we just say execution unit, you'll hear them say that, is because typically these things do more than one thing. So typically you know, you've got all these, all of these sort of transistors wired together, right? You know, it's all in silicon, but you have to imagine, right? It's this little circuitry, right? And when you've got all of that circuitry in there, there's ways of making it be multi-purpose. Kind of, we're familiar with this in software. You know, you may have a function, it takes a parameter, and it can do multiple things based on that parameter, right? Well, ALUs are pretty typical. So anyway, you drew one of these things, and you were talking about how there's a lot of them, right? You were kind of duplicating that diagram. There's a lot of them in the CPU. And then you were talking about how, like, okay, on the x86, how many instructions do you have? You've got, you know, 15,000 to 3,684 or whatever, right? You pull that up. And then you're talking about how ARM only had maybe 230. And so the first thing that I kind of wanted to talk about here was based on that part of the conversation. So I think there's an important piece to understand here, which is that instructions, the way that we think about them on the software side, so this idea of an instruction where we look at some documentation, you know, if you're a low-level programmer, right, and you look at some documentation for the instructions, those are what we're thinking that the CPU itself is going to do. And that is true. That is what gets fed to the CPU. We write these instructions, and even if we're writing in something like assembly language, they then turn into binary data that the CPU is going to like pull in, right, and decode and turn into something that it's actually going to do. But the critical thing to understand there is that those instructions don't map to ALUs. So in other words, it's not like if you have 1,500 instructions, you have 1,500 ALUs, one for each instruction. Instead, what you have is some number of ALUs, usually fairly small. Like we're talking, you know, in the numbers of 20 or something like that, right? There's very few. And those ALUs are designed to, each of them, do a fair number of things, a fair number of fundamental operations. And we call those things micro operations, typically. Not instructions, but micro operations. And what the instructions that you feed to the CPU are, they're actually, they basically say what series of micro operations you would like those ALUs to perform for you. So when you see something like, oh, the Intel architecture, x64 has over 1,500 instructions, that really doesn't tell you anything about how many ALUs there are. And so let me just give you some concrete examples there, because I know that that's all just kind of abstract what I'm saying. So here's an example of a block diagram. And I used this one specifically because it actually came up later in your video when you looked at that x86 needs to die um,
Mhm.
uh, uh, blog post, which again, I'll just touch on, right? Like I said, really easy to not to be wrong about this stuff. That's an entire blog post. None of it was basically true. Like it's so
Yep.
if you go read that thinking that's something that's true about the world, which you don't, if you don't already know microarchitecture, how do you know? That article makes the rounds. Now that's in your head, and it's easy to be wrong about this stuff, right? And that's why I say it's very easy to be wrong about this stuff. Unfortunately, it's really nobody's fault because there's just a tremendous amount of noise out
Yeah.
there and
Like
not that much signal.
as I said before, I've been nerdy about these things for a while and read and look into what resources appear like in front of me whenever I see them. And your interview with Prime was the first time I heard these pushbacks. It wasn't information that's particularly well out there, which is again why I was so excited to talk to you. I wish I'd watched that before I did my video, because it would have been a very different video, if one at all, because again, like, this info isn't accessible enough.
It really isn't. And again, and the hardware engineers, because again, they're secretive and it's not, I guess, in their best interest to correct these things. They're not out here say like that. There isn't a hardware roaster channel, right? Where it's like a hardware engineer who just like, tears apart all these bad blog posts, right? That's not a thing. I would
Yeah.
watch that religiously, right?
Level
But
one tech's
it's not.
busy fixing KVMs for the entire industry.
So anyway, here is a block diagram that was cited in that one. It's made by AMD. It comes from AMD's own slide presentations, and AMD is actually more open, say, than someone like Apple about what's going on in the chip, to the extent that they do produce one of these block diagrams and show it prominently in their presentation. And what's great about this is this shows you right here how many basically of those primary execution units, those ALUs, and I'm using the term execution unit here because ALU is typically talking about a very specific kind of execution unit. And we can maybe touch on that when I go through here, but generally execution is something that does a fundamental microoperation or something like that. This row right here that I'm kind of hovering over with my mouse cursor, those are the execution units that are in a Zen 4 core. And you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So 14 on the order. Like I said, I said pick the number 20 randomly because I didn't want to single anyone out, but it's on that order. And anytime we open up one of these, it's going to be somewhere around there. It's not going to be 1,500. It's going to be 20 or 14 or 8 or whatever. And they're labeled based on what kinds of things they do. So you see you've got AGUs here. Those are address generation units. You've got the ALUs, arithmetic logic units. You've got BR, which is for branching. You've got the over here on this is the floating point side of the chip. It's really the vector side of the chip. They label it floating point and integer, but really this side does integer as well. But this is what does those sort of SIMD instructions. You ever heard of them? Here you've got
Yes.
your multiply accumulates, your adders, the store, the ability to store things. That's what all of this stuff does. So if you look at one of these chips, you're just fundamentally not going to see any kind of relationship between the number of instructions in the instruction set, whether it's 15 or 1,500 or 15,000. You're not going to see any relationship between that number and this number, right? Because of this top part of the chip right here. Typically in CPU architecture, we call this the front end. And I should say we. We. I don't know this stuff, right? I only know what they tell us about this stuff. So I say they. They call this stuff the front end. And what it does is it turns those instructions into things that can be done by these execution units. So that is why I said before, oh, they do things called micro operations. Why do we have to have this other term, micro operation? Because instructions and micro operations are not the same thing. So the instructions that you write, they go through a decoder, they turn into some series of micro operations. Those micro operations go through schedulers in the chip because, again, these are out of order chips and they have pipelining and they have all this other stuff. So they're trying to execute as much stuff as they can at once and all this other stuff. They go through these pipelines and then they end up executing on these execution units down here. And if you think about what actually happens there, the result is that the entire argument about things like ARM and x64 and which one's going to be more power efficient or all those sorts of things, people end up getting confused about that because they focus on this first part, which is how many instructions there are. And because there was this sort of, original RISC versus CISC kind of stuff, which we'll get into a little bit later, they focus on that and they think, oh, it must be that x64 chips are going to be more complicated on the inside because they have more instructions. But in reality, there really isn't much truth to that. And in fact, you can build quite small x86 chips if you want to, because most of the circuitry that's in there, like most of the die area, is not being spent on things like translating instructions into these micro-ops. It's actually being spent on completely other things. And I should put a little asterisk on that because decoding in parallel is a thing that gets spent on, and it is one reason that you should care. But again, it has nothing to do with how many instructions there are. It's about other things like whether those instructions are variable length and that sort of stuff. And so what you can see when you look at something like this is that really, if we want to talk about differences between things like ARM and x64, we're not talking about those ALUs. It really doesn't matter. And you're going to see a very similar number and type of those no matter what you look at. And but I don't want to go on for too long.
Can we keep that open? I do have some questions if we can go first.
Let me just show you one quick thing first, and then I'll stop and you can go. So here is, there's a Twitter account called Cardiac, C-A-R-D, or Cardiac, like, who maintains some best guess block diagrams for how CPUs are structured. So you can see again here, you've got like the different like ALU types here, right? And you've got which ones can store data and that sort of stuff, like I was pointing out before. This stuff down here is the same row that I was pointing out, right? You can see them again, address generation unit there, and ALU there, the branch handling there, right? Whatever. So this is that same diagram for the Zen 4, but just maintained by people in the community who tried to figure out based on, again, reverse engineering, a little bit more detail than what they give on the AMD slide presentation. If we open up the same one, so the same guys, maintains this stuff for Firestorm, which is the ARM core that's in like an M1, right? Here is the same thing, right? You look and you're like, here are the same roughly, maybe there's a few more. If anything, there are more ALU kind execution units on here, right? But it's roughly the same order of magnitude for the things that are in here. And again, like if anything, you're seeing more on the M series because it's a more sort of like overpowered chip for what it's trying to do, right?
And they also do actually, from my understanding, they do stuff a lot of specialized stuff in it. Like they have more things that are for just like x86 emulation with the Rosetta crap. And I don't know how much of that's like on the chip versus is purely software, but yeah, I know they're trying to sneak things in.
We can actually talk about that. I did pull some references for that because you mentioned that in the video. So we can get to that later. But in general, the reason there are more of these is not because of that. It's because they want more power, right? They wanted a powerful chip. So they're like, we're going to spend a lot of money. We're going to dedicate a lot of die area. We're going to have a lot of execution units, and we're going to feed those things, right? And there are some reasons why some of that is easier in ARM, but they have to do with what's up here, and we'll talk about that a little later. But anyway, I just wanted to show that really quickly. So when you look at these two, right, and if I go back one more time to that Zen one, it doesn't look that different, right? And so again, number of instructions is not really the thing that you want to focus on when you're thinking about that. Okay, so let me bring up that diagram because you said you had some questions, and
Yeah.
and just so I just want to give that
So
background before we go any further.
super, super helpful and gives us a really good like area of understanding that we can discuss from. To just make sure my understanding here is correct, there is effectively another set of instructions, the microtasks that exist underneath assembly, and any given like instruction you're giving, like an add instruction, can map to many different things underneath that we don't know anything about or have any insight into as the developer writing the assembly code.
Yes, although I would say we do have some insight into it, and we can talk about that in a second. But yes, so if you were to take something like an add instruction, for example, an add is one of the most simple things the CPU can do. So if you were to do an add instruction that was going to add, so again, I don't know how, it depends on the knowledge level of assembly language programming of people on the stream here. But there's this concept of register names, right? So you say, I want to do an add, and you say, I want to add this register to this other register or something like that. In x64, there's obviously the equivalent on ARM as well, and so on and so on. If you were going to just add two registers together and put it in another register, get the result out, which maybe goes back to the same register, maybe you've got a ternary op, goes to different register, blah, blah, blah. Point being, you're doing adds inside registers only, register names. That would almost certainly, and definitely in x64, but on most things, that will turn into just a single micro-op. Because it's so simple that it can be done just by one arithmetic logic unit with one operation, right? Mm-hmm. However, if instead you were to do something that is allowed in x64, which is you were to do an add of a register to a memory location. So you have not loaded that memory location into the CPU core yet. It's still sitting in like a cache somewhere or out in memory. You're saying go fetch that and then add these two things together. Now it does not turn into a single micro operation. It turns into multiple micro operations because those micro operations are going to do that fetch and then do a single micro op for the add at the end. But there will be more total micro operations issued for that thing because effectively what you've coded there is a load and then an add. And it will turn into those sequential steps when it flows through this pipeline. Specifically, when it gets decoded right here, it will be turned into more than one micro op that will then flow through. And so that is how this works, right? And depending on the complexity of the instruction, that's what you'll get. You actually mentioned this in the video, in fact, when you were looking at that x86 needs to die article. They mentioned this mpsadd dbw, however you want to say that, mpsaddbw instruction. This is mentioned in the article as kind of like, oh, how x64 is so ridiculous, right? It's got this ridiculous instruction that does compute multiple packed sums of absolute difference. How is that? That's so silly, right? Well, what I did here is I just pulled, let me bring this up in a sort of a bigger window here. I pulled there's actually a really great project that these guys wrote a thing called NanoBench, and it basically is like a systemic way of interrogating what kind of micro-ops are done for various instructions. So I pulled the page on that particular instruction. And what we can look at, we can pick one of these CPUs here. I happen to have a Skylake in my streaming machine, so we can look at that particular one. But what you can see here is it says what it's actually going to do. So this port usage thing here actually tells us, and in fact, number of micro-ops up here would tell you too, but this is kind of a more interesting one for various reasons. So that's going to turn into two separate micro-ops on that architecture. If instead I was to look at one of their most recent ones, like Alder Lake P, right, you can see that that's going to do two, but it's going to do them in a different pattern, right? It's going to do one here, one there. If I was to look at the E cores, which are the smaller ones, right? Actually, that's interesting. I was about to say they should be different, but maybe I'm on the wrong one here. Yeah, it's 3 on the E cores, right? And so when you look at one of these instructions, it's like there's not a single unit that does that thing. They're just going to figure out like, okay, across all of the computation resources that this chip has, we're going to figure out a way to execute this instruction as efficiently as we can. That may be 2 microops. That may be 3 microops. There are ones that take 10 microops, for example. And that's fine, right? It's not a big deal to support these things because they're not actually designing any specific part of the chip just to do that. It's just going to be in that sort of microcode, if you will. So anyway.
This is fascinating. So, and to try and boil it down for my simple JavaScript brain, if you write a single instruction in assembly that is add, and you give it 2 raw values, it can do that simply in one instruction. But if you write the same, or it can do it in one task, not instruction. Instructions are what we write, tasks are what it does. Is that a fair way to split the terms?
Just the corrector. The term they use is microop.
Okay.
Micro operation.
Cool. So my one instruction, if it's 2 like bare values, could quickly go through 1 microop and come out. But if one of those values was actually a memory address that I had to read from, even though the instruction is still one instruction in my assembly code, it is now doing something meaningfully different on the architecture level in order to go down a different pipe, go read that value, and then bring in the value before putting it down the right microop.
Absolutely correct. And again, just to emphasize, this is not fixed. It's not an aspect of ARM or x64 or anything else. It changes per CPU core. So on a Zen 4, it might be multiple microops. On a Zen 5, suddenly it's 1 microoп. We don't know. Like, that is just, it depends how they designed the hardware and what its capabilities are. And the designers of the hardware, they're sitting there thinking about this all the time, right? They're like, we've got all these things we're trying to do. We know what kind of benchmarks we're going to be run on, and how people like you and I are going to evaluate this chip. Do I want to buy it? Our gamers going to buy this thing? Our data center is going to want this thing. They're thinking about all those benchmarks, and they're deciding what the breakdown of these execution units should be. How many of them should there be? How many of each kind, right? Because how many integer multipliers do you want on this chip or whatever? Well, they can always decide to spend more die area or make more trade-offs to get you more of a specific thing. Is that a wise choice? Is it cost benefit to them? All that stuff. That's what they're thinking of. And then based on those decisions, different instructions will take different numbers of microops because that's the minimum they could figure out to get the chip to do that thing. So that's what it does, right?
Is it also fair to say that on a given CPU, there are multiple different answers to the question of how many microops a task can take? Because it could go on the P cores versus the E cores, the power cores versus efficiency cores, I think is what the letters are supposed to stand for. Most processors now have been going in that direction, where to make the battery efficient and to not pull 300 watts constantly, there are cores that can do most tasks more efficiently, but then they have the powerful cores for when you're just hammering your CPU. That sounds like the actual mappings can be entirely different depending on which of those pipes your assembly is going down.
Yes, they are. They can be dramatically different, and you're absolutely correct. In fact, that one I just showed, the E core and the P core had different number of micro operations, and so it's just like, look, the P core has a more powerful execution unit, maybe that can do a little bit more in this particular way, and so when that micro-op executes there, it can do more of the total operation. So it only needs to do 2 total micro-ops to get it done. The E core, it can't do as much in a single cycle in that execution unit, whatever. So it's got to do it in 3 steps, right? And that's totally normal, right? And also very common from revision to revision, right? Like when you go from an M1 to an M2 to an M3 or an M4 or whatever, or a Zen 1, Zen 2, Zen 3, Zen 4, same thing. Like we may change, like, oh, this used to be more expensive, or sometimes it goes the other way. So it's like, oh, this used to actually be done completely in one, and now it's not because we wanted to optimize some other thing and this instruction wasn't that important, or blah, blah, blah.
That did actually just happen. Like, again, nerd about all sorts of hardware stuff. The base M4 MacBook Pro gets worse performance in a lot of like heavy audio video software. Like I know you can have a smaller number of tracks open in Logic Pro and a
Oh,
base M4 MacBook Pro than a base M1 MacBook Pro because they shifted to have more efficiency cores and less power cores because one of the features people really liked about
okay.
the machines was the battery life. And they realized, oh, our efficiency cores are more than powerful enough for most tasks. We should just have more of those. So the likelihood you even have to spin up the power core or the P core is less. And now they get even crazier battery. They're advertising like 20 hours. But if you're buying it for the power specifically, you're getting shafted unless you get one of the higher end models now.
It's everything in hardware design is a trade-off, right? It is always that where it's like they have a certain amount of die space and they're going to spend it on something, and if their market dynamics say that e-cores, or I guess Apple calls it big little, I guess,
Yep.
or do they call it big little? I don't know. They're Firestorm and Ice Storm, I think, right? Is what they call them. But if they say they're going to have more of the lower power ones because that's what the market is going to want, then yes, some people are going to be unhappy because like they would have preferred way more power cores, right? But that's just how it is.
Absolutely. Okay, this is starting to click. And part of me is just feeling rage because I've gotten so much crap throughout my life for using a language that is virtualized when I could be writing things that compile to real native instructions. But in the end, instructions are all a mirage. This whole thing is like assembly is a language pre-assembly almost. There's actually a question I got in chat that I thought was interesting, and I'd love your take on it before I give my less good one. Why is it that we write something like assembly that is an instruction set that's abstracted and then rely on the processor to do the mappings? Why wouldn't we write the the micro ops ourselves?
So it's a great question, and I can say there's probably two ways that you want to look at that. So the first way that you want to look at it is I'll give like I'll give the JavaScript answer first, actually. So that should be familiar to everybody. There is a benefit in having a standard that is not hyper specific to a particular hardware design. You don't really want to recompile 100%. Well, maybe some Linux users would disagree, but you don't want to have to recompile 100% of your software 100% of the time and retest it on every piece of hardware, right? So if
Not
we
just
were to
Linux
say,
people, Rust people as well.
okay, well, yeah, okay, but you know what I'm saying, right? Like, so in general, we would like some binary stability. And so the high level abstract reason you might not want to code to that is because literally you would have to have two different binaries, one for your P core and one for your E core, as we just said, right? Because they're different micro ops, right? Just even on that one, we were looking at Alder Lake. So just one Intel chip in your laptop, but because there's different cores on it, you would have to have two different binaries running on those two different core types, right? So there's a high level abstract sort of like just programmer view of it that there's a reason why you wouldn't want that. But there's a deeper hardware reason why you might not want it either. Micro operations are literally just whatever that CPU core most efficiently is going to do for a particular thing you want to accomplish, like an ad, right? And we don't necessarily like even if you just think about how we do things in the software world, we don't necessarily always want to send when we're sending something, like when we send something to the CPU, right? We don't always want to send over a channel the literal thing we were trying to do. We don't send raw image data, right? When we go to look at a photo, we send a compressed representation of that image data because it's way more efficient to do that. And then when it gets to the place that actually wants to view the image, it gets decompressed. Well, ICEs like ARM and x64 and that sort of thing, you can almost think of them at this point as a a compression language for these micro ops, meaning we need a compact way of just saying, look, I'm trying to do an ad here between a register and a memory location. I want to express that in as few bytes as I can. And then when that gets down to the actual CPU core and it's ready to work on it, it can expand that out into several micro ops if it needs to. But that would still be more efficient than me actually saying what all the micro ops are. And so there's another component to this, which is that if you design a instruction set intelligently, you may also be able to get a more compact representation of what actually has to happen. And so you wouldn't want to force it to have all those micro ops. And just to give you a little bit of insight into why that's might be possible in hardware, if we thought about even that simple case of doing the add with a memory location, well, think about the steps that are going to happen inside the CPU. It's going to have to go fetch that memory address. It's going to have to put that somewhere. It's going to have to then take the register that had the existing value, and then it's going to have to add those two together, and it's going to have to put it in another register. Now, all of that has a bunch of redundant information in it. You know, because you're executing this add with a memory location, you know that whatever you fetched, you're then going to add it to this other thing. But if you imagined us having to send all of the micro ops down, we'd have to put in that redundant information. Hey, when you fetch that thing, put it here. And then when you do the add, grab that and add it to the thing. Well, the grab that part was implicit in the original version because you knew that you were going to add it to the thing. The CPU just knows I don't have to tell it, right? It just picked a place to put it and I don't have to care. So there's a bunch of redundant, when we have multiple steps, there's a bunch of redundant labeling that goes on. If we were to tell the CPU that, it would then have to process all of that extra information, which means more bandwidth through the front end, more decoding has to happen, more, right? And so you do get a savings by not encoding the micro ops directly, depending on how intelligently the instruction set was designed. And, that's a hardware reason you might not want it.
This is starting to click. The compression part made a lot of neurons fire in my brain that are making this all come together now. Weird analogy to get to here, but I do a lot of Advent of Code, which is a programming leak code challenge that runs every year. And a thing we often have to do is memoization of some form, where we have a specific key and it's mapped to a certain result. Like the problem that I just did, it's like rock. It's like a weird quantum rock problem where every time you blink, a rock, depending on one of three states it can be in, becomes multiple rocks. Okay. It's like if it's an even number of digits, it gets split into two. If it's a 0, it becomes a 1. If it's a 1, it becomes something else. But there's like different cases for it. The first part of the problem, you have to do it in a certain number, or like I think it's like 25 runs you have to do on it and get the number of rocks on the output. That one you can just brute force raw. It works in like milliseconds still. It's super simple. Part 2 is now you have to run it 75 times. And the moment that where it clicked for me was, the order of these things doesn't matter. The storing of all of this is way too much data. All we care about is what one number becomes. This number becomes one of these 3 different things. If we have to do it 72 times, we just multiply it by 72 now. And that realization meant, I can map every single one of these instructions that are just like a single number to an object that is like a dictionary, just tracking all the things it converts to. And then I can pass a much smaller value over to my machine that does this, and it will give me back a much smaller response using that map to figure out the more complex parts that normally would have had to be encoded in the instruction. I'm able to significantly reduce not just like the amount of data that I'm writing in my application or the length of the instructions. I'm reducing how much back and forth there is. I'm reducing how much complexity there is in the instruction that I'm passing. I'm reducing the amount of work the CPU has to do because it has a quicker path to get that response. Instead of having to read each chunk to figure it out, it takes the one instruction and then maps that to all of the work that it has to do. It is actually faster just in terms of the data being passed back and forth to do it that way. That makes a lot of sense.
Yes, and this is, again, also why, when we talk about x64 versus ARM versus RISC-V and that sort of stuff, and, I come on streams like this and I say like, there's these misnomers, and I show like the ALUs or that sort of stuff. So yeah, there are a bunch of misnomers, or I said there are misunderstandings, I guess, about what affects what, but it isn't true that ICEs don't matter, because these kinds of choices about how did you structure the encodings of your instruction set? They do have consequences for how big things are when they are, when you actually have to represent a program, consequences for how hard it is to decode it, or how hard it is to decode it in parallel, or other things like this. And so really that part that's talking about going from instruction to what the CPU will actually do is part of the thing that differentiates a RISC-V from an ARM from a x64, because it does matter to some degree. It's not one of the most important things, but it does matter to some degree, and it's for those reasons. Yeah.
On that note, I'm resisting the urge to make a lot of jokes about Java being the optimal assembly language right now, but now that we're thinking in terms of the different instruction sets almost as like a front end on top of the micro optimization, the micro op architecture that exists on the processor, the scheduler, and all of the pieces that do this right based on the assembly instructions you give it. What is the difference between these different instruction sets, and how does that affect things like the architecture of the chip and the potential performance and all of the things that I was trying to explain incorrectly in my video?
So I guess let me comment on one thing there about Java, and then we will move on to that question.
Sorry with the bait, I had to.
No, I actually think there's an important thing there, which at least I try to get across, so I want to take this opportunity to get it across. Picking a language to program in is a lot less important, in my opinion, than programmers being educated about instruction sets, like this kind of stuff we're talking about today, and actually keeping an eye on whether the languages they've chosen are producing efficient instructions for these architectures. Because if you program in Java, but you have a pretty solid understanding of microarchitecture, and you're keeping an eye on what your Java, JIT is doing, and you're like, it's producing pretty reasonable, code for what I need it to do, you're not going to have a problem, right? But if on the other hand, you just assume that everything's fine, that's how you get into these bad situations where people are making the software that's like, it's just generating like, thousands more instructions than it needs to because of too many layers of abstraction and some bad ideas about what practices to do and so on. And so I feel like the important part is not what language you started in. It's connecting those dots of like, just having some experience with looking at what the CPU actually has to do for the things you're writing in your higher level language, and making sure that is somewhat sane. That is the important part. And to the extent that your language choice matters, it's just about making sure you're choosing a language that isn't doing really bad stuff there, which some do, right? Some are just spending way too much time.
Can I go down this rabbit hole a bit longer? Because I have things, and I actually might be able to introduce you to some cool stuff that's going on here, because this is the world I live in. So the other angle here that's important to know is, like, on one hand, yes, if you're thinking deeply about the code you write and looking at the output of the code you write, even looking at like the VM that you're running that code in, nobody does, but if they did, awesome. They're still going to be limited by the next like order of abstraction, which is the libraries they're using, the packages they're pulling in, the external dependencies that they have no control of the code for, much less the like levels of optimization that exist within. And there are certain libraries that out of necessity do things that are very complex, that are hard to optimize. There's a really cool thing going on in the JavaScript world right now. Have you heard of the Hermes project?
Mm-mm.
It originally started as a new runtime for JavaScript focused with a very specific need. It's by Facebook and Meta. They wanted to improve the startup times for React Native apps. The performance of React Native app on the JavaScript side was decent, but the actual spin-up time was slow because V8 just took so long to spin up, get all of its like registers in order, allocate memory, and all of that. Hermes was optimized to cache the like JITted state so that it can restore it way faster. So the startup times are way better with a slight cost to certain other things. It's not meaningful. It's like 5-10%, but the startup times were like 3 times better. So huge win there. They wanted to go further though. And with assistance from Amazon, who's actually been leading this project, there's a new rendition called Static Hermes, which is a compiler that requires you to use a typed subset or superset of JavaScript, either TypeScript or Flow. And then it will use the type information there to compile assembly out of your TypeScript, which sounds like, oh, we should just run everything through it. That'll never work because nobody's going to write perfectly typed strict code for application code. But what I'm excited for is for some of those heavier dependencies that we rely on, maybe even something like React itself, to be written in a way that it could be assembly, and we could be pulling in effectively an assembly dependency in our JavaScript code, and everything interops on a language level natively, and ideally in the runtime natively as well. And we're getting so close to that magic. It's like happening, and I'm really hyped for the future of it.
Well, and the more that those sorts of things happen, the more opportunity there is for people to look at this stuff and go, oh, this is really inefficient. Let's optimize that, right? But when it's this huge kind of diffuse thing and nobody really knows when the assembly language is getting generated in the first place or whatever, and no one's focused on it, right? Then it just kind of remains slow for quite some time, right? So,
yep.
Yeah.
And there's so many things like that. Like when you run a function a certain number of times in V8, it gets jitted so that it can be hit faster because it's now like compiled something closer to native assembly out of it and caches that. But how hard does it cache it, and how often do you actually hit that cache are big, vague questions that don't have good answers, especially in Chrome. There's a fun flag you can turn on in Node where you can tell Node to store the cached JITted output, and it actually makes Node's spin-up times like 10 to 100x better. Companies like Vercel are working really hard to automatically do that and cache the JITted output so that it doesn't have to send the raw JavaScript code to spin up a Lambda every time when it can cache the binary instead. We're just starting to find these things in the JavaScript world. But like for the first time ever, we're starting to look at the native like assembly and instructions that come out of our JavaScript code and think about it deeply as a web dev world. And it's actually really exciting. And I'm hopeful that us talking about this to a web dev leaning audience, like the ones that are watching this now, I see you there in chat. I know that you're here for the JavaScript stuff. I hope that we can get more people excited about these things going forward because it's going to be more important than ever. And I think there's going to be a niche discipline within web dev of the people who know enough about these things to take the core dependencies powering the internet and make them 100 times faster.
The opportunity is definitely there because, again, the real great part of understanding the actual stuff the CPU is going to do is that is what lets you know what its performance will be. Once you know fundamentally what the CPU is going to do in terms of microops, you more or less know exactly how long somebody's going to take. Modulo some things about like, well, depending on like, your fetching patterns and things like this, is it going to come out of the L1 cache, going to come out of the L2, those sorts of things. There's some things about data flow you have to learn as well. But in terms of understanding the actual computation part, once you kind of know how instructions turn into microops and what they're going to do, you have a pretty good idea of how fast somebody's going to run. Whereas if you just look at something in a high-level piece of code, you really can't tell because it doesn't really have anything to do with the CPU at that point. So there's no way to have that kind of mental model. But okay, so you asked a question though, which is
it was about
what are the differences? Yeah,
we can go to that, but there's another question that I think might help here. Okay. I'll let you pick what we do first. The other question was, what is a cycle?
Okay. So what is a cycle? Meaning like when we say like that a thing is running at 4.8 gigahertz, like that.
Yes.
Is that
like what is a CPU cycle? Like what is done in one? Where do we say a cycle starts and stops? Like it feels like such a vague term now.
So I feel like, this is one of those places where I really have to say that it would be better asked to a hardware engineer, because I can only give you the absolute hugest bird's eye view, right? But my understanding of what a cycle is, or rather why do we have a cycle, would be maybe the better question. Is like why did that become a thing that anyone says or cares about, this concept of a cycle? Why don't we just talk about how many nanoseconds a thing takes, right? Well, my understanding is that in order to design these sort of complex pieces of logic, they need to be bucketed into steps in some kind of a way where you coordinate the handoff of data between those steps. So in other words, you kind of have this idea of almost like a factory assembly line, like somebody's going to do a thing and then they're going to hand it off to the next person and they're going to do a thing. And with the way that the hardware designers design stuff, for whatever reason, and again, I I do not fundamentally understand electricity and the way that these chips work. This is why I say it'd be a better question for a hardware designer. For whatever reason, it is not the way it is done, or is not a good idea to just have electricity flowing through the chip willy-nilly and producing an output. Like, that apparently is not how it is done, right? A hardware engineer would be like, are you crazy? No, 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 right? Instead, what they do is they have essentially a timing, a piece uh, like a piece of the silicon is for timing, and it sends out a regular pulse that's like, this is a clock cycle, right? It's like tick, 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 tick. And each core nowadays typically has its own one of those, because the cores, if you've ever seen like this idea that cores can boost, right? So there, used to be you had one clock rate. Now there's like a range of clock rates, right? Lower power states, higher power states, so on. This like periodic tick is basically there to, when the CPU does a little bit of work on something in one part of that assembly line, the tick is what then hands that work off to the next part. So you have this like pipeline of things that are going to be done. Let's say it's 14. You talk about pipeline stages. Basically, the CPUs are made to sort of like go in this order of doing things. Each one of those handoffs happens on a tick. So when you actually look at a CPU pipeline diagram, which unfortunately they don't ever publish, I'm going to have to think about where I would be able to find something like that. Let me see if I can find one for you. Because the block diagrams that I was showing, those are telling you what the logical sort of series of steps are that are going to happen for this thing. But let's see, AMD bulldozer pipeline diagram. I think I saw one of these a long time ago. Let's see if I can find one. But they're very hard to find for any modern chip. I don't see it here. But they're these series of pipeline stages, and they are things like, oh, in this pipeline stage, we're going to do, like, we can do some decoding of this instruction. The next pipeline stage, we finish some decoding of that instruction. The next pipeline stage, we fill things from the micro-op cache. We do this thing. In the next pipeline stage, we can do this, right? Blah, blah, blah. And so the cycle is the thing that moves stuff forward in those pipelines. And so if you take a look at this block diagram, which is not a pipeline diagram, but if the sort of the best I can do here, because I don't have one of those, is you can imagine each one of these things that is drawn on here. They have various kinds of pipelining inside them. So like maybe one of these ALU units has a couple pipeline stages. So it does a little bit of work, that it does another little bit of work, that it does another little. So it feeds forward that way. And like maybe this like integer renamer has like one pipeline stage to do what it's going to do. And this decoder has like two pipeline stages to do what it's going to do, or whatever. So when you actually are talking about the CPU executing things, it's sort of flowing through this in steps. Tick, 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 tick. And those ticks are on the clock cycles. Now, again, I can't give you any better answer. You really need a hardware engineer. This is a question a hardware engineer would answer. It's not a secret, right? So this is one that would answer, but I just don't have the kind of, I'm not a electrical engineer, so I don't know. So I can't help you with that part. But so why they have to do that, I don't know. But that is what they have to do.
One of the best possible answers to that question is, I'm not an electrical engineer, so I don't know. I think that helps clarify. It's like one of the things that I'm trying to figure out, and I'm sure a lot of other people watching are, is how much of this should we be like trying to know? How much should we like aspire to know? And how much like doesn't matter at all? And it sounds like what a cycle actually is doesn't block you from doing the types of educational work that you do. You're able to inform people like me to a much greater level on how this stuff works without having a good definition of what a cycle does. To analogize this to something like React, because I'm sure that's what my audience is familiar with, most of the best React educators in the industry can only vaguely describe what the reconciler does. I know that because I'm one of those educators, and I can do an okay job of describing it. So yeah, just like even to be great at the craft doesn't mean you have to know every single one of these things. It is basic as what is a cycle sounds. It doesn't actually, like the deeper understanding isn't blocking you from writing better code and making better, more performant applications.
Exactly. And so taking it up one level and saying, well, what is the part about a cycle that we care about, right? Well, that part's pretty easy. there's this pipeline. Like I said, the CPU has to do this pipeline to execute instructions, and the pipeline is advancing at that cycle rate. So what that means is that when we look at, say, those micro operations, remember I said like, oh, this takes 3 micro operations? Well, a micro operation, the fastest a micro operation can actually execute is in one cycle, for example, right? And it's not actually executing in one cycle. There's sort of a whole other category here. This idea uh, of how long does it take something from start to finish to execute versus your mental model of how long something takes. I realize this is really kind of getting off in a different direction that has to do with throughput and latency analysis, but I'll just say really quickly, just for people who are interested. So think about network latency versus network bandwidth, right? This is something I imagine a React dev would be familiar with. If I need to go fetch something from the server and have it come back to me, that is potentially a long time. 40 milliseconds, 30 milliseconds. I don't know what it is. Depending on the data, it could be even more than that, right?
That if you're doing a network round trip, it's going to be a lot more than that. We're talking closer to hundreds.
So hundreds of milliseconds then potentially, depending on what you're doing, right? Well, if I was to ask for 1 byte of data, just 1 byte, right? It would take that long. I asked for the byte, it goes out, it comes back, it took 100 milliseconds. Well, if I'm only getting 1 byte in 100 milliseconds, in a second, that would be 10 bytes or 10 bytes a second, right? Nobody would ever be okay with that as your internet bandwidth. If you had to download files at 10 bytes a second, forget it. So what's going on there? Well, the answer is
I think that what's going on there is you're on Comcast.
Okay, well, yeah, there's that too. But what's going on there? How do we get more than that if we know that it takes this kind of round trip? Well, the answer is because we send many things at the same time, right? When we talk to the server, we say, send me a bunch of stuff. And then it just starts sending. It doesn't wait to hear back from you, right? It's pushing a bunch of things down that pipe, and it's just assuming you're going to get them. It doesn't wait for the round trip, right? So that whole concept right there is exactly the way that the CPU pipeline is working as well. It can start executing an instruction, and it may take 14 cycles from start to finish to get that thing done, even if it's very simple. But because it is pipeline, because it's starting many of those as it can, every cycle it's decoding more and pushing more in. It's not waiting till the end of it. So when you look at a single cycle, a single micro-op can execute at around the speed of 1 per cycle, oftentimes, because the resources of the CPU are such that it'll be decoding enough things and it'll be doing 1 every cycle. Now, really, when we look at the total performance of the chip, it can do even more than that because it's got multiple execution units. So if we can fill more of them with more micro-ops, we can do way more than 1 at a time. We can do 6, 7, 8 sometimes, depending on the circumstance, right? We could do a lot of them. And so really all we need to think about in terms of cycles when we're doing this kind of hardware analysis is, okay, that is a fundamental clock that means something on the CPU side. We don't really know exactly, because unless you're an electrical engineer, why they're doing this way, who knows? They're just, trust them, they know what they're doing. But we can think of that as like, all right, if I look at this instruction stream and I know it has to do these micro-ops and they're dependent in this way, and I know that my cycle, the speed of the CPU is this many cycles per second, then I can very accurately predict, okay, it will chew through this in about this amount of time. So we tend to think about cycles in that way, like how many of these micro-ops could be consumed in how many cycles. That's all we're really thinking about. And why the heck you need these timing crystals on a chip to bucket, and to hand the stuff out. An electrical engineer would easily be able to tell you. I have no idea.
Someone in chat gave a pretty good analogy for it that I think really helped it click for me. It was, I believe it was Hooper Nikedes in chat. The analogy was comparing it to an orchestra, having a conductor, making sure everybody's moving in sync. Or I would go a bit further and say something like air traffic control person for an airport, where it doesn't matter how many planes you can fit onto the tarmac or how fast a plane can take off. What matters is how much time is there between the planes, making sure that one's ready to go as soon as the last one takes off or lands, and orchestrating, making sure everything is moving constantly.
Yes.
And it's not the speed of any one part's movement, it's how fast does each step get gone through. The other thing that's firing in my brain is that, like, with the little bit of game dev I've done, I think a lot about ticks and like frames in every frame, trying to process like what happens next. This feels a lot like that too, where it's like every frame I advance one to many things forward based on what's changed in that time.
Yes. And so like beyond that, it becomes an electrical engineering question, right?
Yes. I am very happy with this answer. It seems like Chad is also relatively happy with this answer. So is it time to dive into what the hell is the difference between ARM and RISC and CISC and like?
Okay. Yes. This is always a bit tough, right? But I'll do the best I can. So, okay.
You won't do worse than I did.
Okay. So let me just. I guess let me just start by showing something pretty straightforward that hopefully will clear up a little bit of the high level misconceptions here. So on that video, you were talking about the number of instructions. I think in RISC-V, I think you pulled it up. It was like 40 or something. And you were talking about how it doesn't even have divide, right? Like something as simple as divide, not in RISC-V. I don't know if you said it wasn't in ARM as well, but right, like there was. Sorry, go ahead.
Yeah, I knew that because or another tech YouTuber I love, Low Level Learning, he became part of our friend group because he did a YouTube video that had an ARM CPU with an arrow pointing to it and said, "Can't do math." And I thought the thumbnail and branding of that was so good that I reached out to him. And now he's like a good friend and might even be watching live right now. I haven't seen him in chat yet, but he usually stops by. So I know that more about the branding of his video than I know it as like a fact. But that was the main point of the video is that chips like ARM chips don't even have a division instruction.
Okay, so I'll try to correct that misconception here. I'm not 100% sure where it comes from. I have a guess, so I'll say what I think it is later. But so let me just show you something here, and hopefully this will be something that's compelling. So I've opened up Compiler Explorer. I don't know if people are familiar with this tool. It's a web tool. It's really great. Basically, what it lets you do is it lets you type code. You can actually pick a number of languages if those languages have the ability to compile to assembly language. And you can type code in the left side. So right here, I'm going to change this into a divide, 1 over the number that's passed in, right? And this is C, but hopefully everyone can read this. It'd be the same in basically any language, right? It's just a function that takes an integer and then divides 1 by that integer.
I actually only write Haskell. I have no idea what these things are.
Okay. All right. Besides functional programming, but even functional programming, it's a functional program.
Yes, it's a function. Yeah, no values are being defined. I'll take it.
No side effects. No side effects. Functional programs rejoice. And on the right side here, I can pick a compiler, and it will show me what the output is. And I can even put switches up here. It's a really great tool made by Matt Godbolt. It's fantastic for educational purposes. It's one of the best tools for education that I've ever seen made for this sort of thing. It's fantastic. So here is the assembly language output on the other side. And, we don't need to go over what all this stuff does because this is not an assembly language learning stream really, but here is the instruction that does the divide, idiv, right? There it is right there. So this is our function. This is the code for it. And, this is not optimized code. I could tell it to optimize the code if we wanted to, and this would get smaller, right? And it's going to do some more like creative stuff with it potentially, but I'm just going to leave it as the debug code so it doesn't try to simplify what's going on, right? Anyway, so there's the idiv instruction, and the suggestion anyway, right, is that like, well, x64 has this instruction that does a divide, and like ARM and RISC-V just wouldn't have that, right? So they'd have to output like a loop, I guess would be the implication, I'm assuming, right? Is that they'd have to do the divide by some kind of series of instructions, right? I mean, I guess, I'm not sure what, you can tell me what did you think it meant if they didn't have a divide?
I thought what it meant is they hack it with multiplication, but.
Right, okay, so there you go. So it does some different multiplication stuff, or who knows what it does, right? But what we can see right here is if I can go pick actually an ARM compiler. So I don't know, I'll pick ARM Clang. Well, that's 32-bit. Let me pick a 64-bit version just so we can stay on 64 here. So here's 64-bit ARM Clang, and I'll just do that. So this is going to compile for like ARM 64, right? So like if you're compiling for an M series Mac or something like that. Well, what you can see is divide instruction, right? Right there. It's called sdiv, and that is just, it's very similar to the idiv instruction, and it does a divide. Exactly like the idiv instruction would do. That's ARM assembly, same thing. Now, if we go ahead and we can pick RISC-V, right? So here's a RISC-V compiler options. I'll pick a Clang again for that. So here's a RISC-V Clang compile. Taking a little while. Here you go. And there's the div-w instruction, right? Which is the RISC-V divide instruction. So hopefully, like just by virtue of seeing it with your own eyes, everyone will now believe me when I say that actually there's no such thing as like a modern like desktop CPU that you would like use, like that you would buy today in a laptop that doesn't have a native divide instruction, right? They all do, whether it's ARM or RISC-V or x64, they've got it. Right.
Are we sure the div here stands for divide and not like div in HTML? We could just be putting like HTML in our assembly here. Like, are you sure?
Yes, that's a good point. But you can see here the documentation for the RISC-V div instruction here, and it says that it will divide the lower 32 bits by the lower 32 bits of the other register.
So
right?
Now what I have to reflect on is the fact that one of my good friends is somebody I only know because of misinformation he spread on the internet. So, Ed, we have some beef to resolve. No, actually, though, I'm so excited to send this to him because he will make a follow-up video about this. I'm almost positive he's gonna love this.
Well, I'm sorry to have created a beef, but also I guess not sorry because that makes for great YouTubing, right? There's nothing better than a reaction video, I guess, that kind of thing.
Seriously, though, props to you for making something as traditionally understood as boring as architecture and instructions be entertaining enough for us to do like many videos on. That is an accomplishment in and of itself. And I, as a nerd of these things, I appreciate it greatly because I don't get ways to talk about this.
I that's what I try to do, right? I try to make it interesting because I would like people to know it. But so anyway, what's going on there? Right. So because it's right there. So if anyone had looked, they would know it was there. Why? Like, how did that get spread? Because I do think I kind of understand why. So what you have to understand about some of these licensable architectures like ARM and RISC-V is they are trying to sell. I mean, RISC-V is not really sell in the traditional sense because they're not, they're an open ISA. But they're still trying to sell it in that they want it to be adopted. Like nobody spends the time to make an instruction set architecture and then doesn't want people to use it, right? So
I get called a shill being paid to sell React all the time. Nobody makes money because React is more popular. If anything, it costs more money for the team to maintain it.
So you want it to be used. Doesn't necessarily mean you're getting paid, but you want it to be used. So you're trying to promote it, right? And one of the things so contrast that with x64, it's Intel and AMD's thing. They just define it and they ship the chips. They're not trying to sell it to anybody. In fact, they prevent other people from using it. So they're not doing that, right? ARM and RISC-V, because they are trying to promote usage of this, they want people to use it. They want it to be used as widely as possible. They don't just ship a single definition of the ISA. They don't just say, hey, this is the entire ISA. Now, to be fair, Intel doesn't really either, because when we say things like, does this chip have AVX 512 in it, right? So yes, this one does. No, this one doesn't. So there are sort of this idea of partitioning parts of the ISA. So, but we'll put that aside for now. Even just the base ISA for ARM or the base ISA for RISC-V doesn't really work that way. Instead, what they do is they define like the minimum set of things that could do like anything, right? And then everything else is a quote unquote extension. So for example, in RISC-V, I think it's called the M extension. and it's for multiplying and dividing. And let me see if I can actually pull this up for you here, because this is the risk manual that I have here. So division. Let's take a look.
I'm just so amused that like I haven't had to use a PDF for documentation on something I was using since I was in college and was taking in it like a programming languages class. Now I have all these fancy web pages with the Algolia search baked in.
I would like something like that because it takes me a while to find these things. It's a pain in the butt. It's called the M extension, I'm pretty sure, but I was gonna see if I could actually find it. Here it is. Yeah. So here's chapter 13 of the RISC ISA, right? And it says M extension for integer multiplication and division. So I think that's where this idea comes from. It's like, yeah, okay, so technically you can build a RISC-V chip without a divider. You can build one without a multiplier. In fact, if you don't support the M extension, you don't have to do either of those things. And there probably are some RISC-V chips that don't. Let's say you've got a RISC-V chip that's some kind of really streamlined, simplified chip for some other purpose that's just not going to be doing any of this kind of arithmetic. It's for just like processing packets in some way. It's not going to be multiplying and dividing. It's just moving bits around in some, router somewhere or something. Well, they just wanted to make it easy to say, okay, we are RISC-V compliant with this, but no M extension, right? And then they don't have to implement these, and they still are technically RISC-V compliant chip. So I think where this idea that RISC chips don't have these kinds of multipliers and dividers or division, I guess, it just comes from the fact that technically it is optional, right? Like you could just choose not to support some extension. But technically it being optional is very different from, oh, the Apple, M series can't divide. Oh, it can divide. Like it's got a divider and it's got a beefy divider in there. So like, off you go. So I just wanted to get that out there, but so people kind of understand a little bit more what's up. So any questions on that before I move on?
So would compilers now have to be more considerate of like which subset of these instruction sets they have access to when compiling? Like if I wrote code in C that expected a certain type of division, does the compiler now need extensions in order to handle that?
Yes, the compiler needs to know things. And as you saw, one of the reasons that I demonstrated this way, I felt like it would be perhaps more compelling to the audience to
actually
or more convincing, I should say. You'll notice I didn't have to set any architecture flags. Just the default compilation for RISC-V assumes you have a divide because, I mean, come on, right? But you're absolutely right. If you wanted your compiler to output RISC-V code that didn't use the M series extension, you would just need an architecture flag that said, hey, this doesn't have a divide, so you're going to have to output emulated divide or something like that, right? So you certainly could do it. But again, it's so common to have this, no one's expecting to run on an ARM chip in a desktop computer or a laptop computer that doesn't have a divide instruction. So the default is to put that out there. There are plenty of things when we do compile that we set architecture flags for. Some of the example I mentioned earlier, AVX 512. A lot of chips don't have that instruction set. So when you compile, you probably wouldn't compile exclusively for an AVX 512 enabled instruction set. In fact, there are multiple parts of the AVX 512 instruction set that you can enable separately. All of that stuff is definitely true. When you do the compile, it has to know that stuff about the instruction set. Divide is one of those things it usually assumes, and it assumes that if you were on some embedded device that doesn't have a divide, you would tell it, right? Like I'm programming for this little potato, microcontroller, and it don't got a divider, right? So
this is super helpful. I did see in chat this might be a good clarifying point. The RV64GC in the RISC-V like Clang option you picked, that G stands for general, and divide is included in the general RISC compiler, which I think makes a ton of sense.
Yeah, and like I said, I don't. So one of the things that people will know if they've ever watched me stream, I never remember all the flags either. So I'm sure right now, if you knew what you're doing, if you were Martin's Mosaico, you would just know, oh, I could put something in right now that will tell it to switch architectures to not have the divide, and it would get rid of it, right? I have to look that stuff up every time. So I don't know. So I apologize for not being able to demonstrate that, but I guarantee you there's a way to turn something like that off, but I never remember.
Not compiling a bunch of games to 5-cent RISC chips with a further reduced instruction set from 20 years ago by the sounds of it.
Yes. So hopefully that's a relatively compelling argument there.
Yes.
Let's now talk though about what the differences in these instruction sets actually are. So first off, I guess I would say, I'll just, as a sort of a blanket high level statement, in general, the trajectories of these things matters probably a lot more than the ISAs. So ARM started out as low power and has been low power ever since. Like it's always focused on low power for the entire kind of history of its existence, if you will. And x64 or x86 as it started out was never that way. It was never meant to be a low power kind of a thing.
Interesting.
ARM also was open in the sense that anyone could license it, and lots of people could compete over different microarchitecture designs that implement, the same instruction set architecture. I feel like it's pretty safe to say that has way more to do with the results you see today than anything we're about to say. So it's not the case that there's no reasons why these things are different in actual practice, but you just have to remember there's a lot of competition and a lot of low power specific competition on the ARM side. Lots of companies trying to do low power chips with that ISA. Really never the case. x64, x86, always pretty much high power. The only time low power ever came into it was the only two players, which is really for the most part, we're occasional like VIA. There's some other sort of also rans on x86 once in a while. But for the most part, AMD and Intel, only people ever did competitive chips. Most of the time they were competing at the high end in the data center. They only lately started shifting to lower power as a focus. And by the way, have been getting better at it. So I would encourage people to remember that business concerns, competition, how open something was, how many people were trying to do a thing, I think that probably has a lot more to do with where you see ARM and x64 today than any of the things we're about to say, right? Mm-hmm. Hopefully that just want to put that out there.
Yep.
Business concerns make a difference, right?
I would have had more doubt of this if it wasn't for the most recent releases by Intel, where they're finally putting out chips that are x86 64 that have battery life that isn't measured in single-digit hours anymore. Like they figured out how to do it. It took them far too long, and it by taking as long as they did, they incentivized Apple to go figure out how to do it themselves. But like Apple tried working with Intel to make an x86 chip that was powerful but low power enough to put into the tiny little 12-inch MacBook, and their frustrations with Intel from that point were what led to them going all in on the Apple Silicon. But that was a business incentive. They had a specific goal for their chips that their chip manufacturing partners could not make happen, so they went their own path, and ARM happened to be the best method for them to go their own path.
And again, it had come up as like so much work had already been done on ARM being low power that it would, they weren't starting from scratch there, right? That was kind of that is more where the low power focus had been, mm-hmm. right? Like I said, even the very first ARM chip was low power. I have been told this is a true anecdote. It came up on a stream before, I think, but there's literally like an anecdote where apparently the first time not the first time, but one of the times that they powered up the original ARM chip when they were developing it, the very first one, which I guess would have been an Acorn computer, or it's back like the BBC Micro people, right? The very first time, or I should say one of the first times when they were working on it, apparently the chip was running, and they realized that they had not powered it. So there was no power flowing to the chip, but it was running. And what they realized was just the residual power, I guess, from other things on the board leaking into the ARM chip. It was so low power that it could still function. This sounds totally crazy to me, but I've been told by multiple people that, I'm probably getting some of the details there wrong, but I've been told by multiple people that apparently this is true. This is like a true thing that has been repeated by that original team. So it started out crazily low power, and it has always had a bit of a focus on low power going forward. So I think that was also kind of the case there. But anyway, so what are the actual differences that we care about today, right? Like, what are the things that you might actually care about? So I do think complexity is a thing, right? So like we'll talk about the thing where it's CISC versus RISC first. It is a thing, but it's a minor point, and I just kind of want to get that out of the way first because I think it doesn't matter that much. It's definitely overstated. So if we look at sort of the original, I even pulled the papers here. Here's like the original PDF paper, a PDF of the original paper where they first talk about what is RISC, right? It's like it's sort of like announcing to the world like this is what we, here's a paper writing up things we've been doing and people have been working on it at that time. There's a bunch of people working on this idea, and this was like a paper where they're like, let me tell you about this thing we've been doing, RISC. And I'm making the case for it, right? And they sort of try to summarize like what are some of the traits of RISC, right? And they say like operations are register to register with only load and store accessing memory. So remember I gave that example of like an add instruction, and that add instruction could use memory as an operation. That's the thing that happens in x64. That's not how it works on ARM. On ARM, it's more like the original sort of idea of RISC, where you wouldn't ever have individual instructions accessing memory. There are specific instructions for accessing memory. So if you want to get something from memory, you do that instruction first, and then you do another instruction you're going to do, right? Operations and addressing modes are reduced. It's like, okay, it's kind of a little, what they actually explain here, it's not really clear exactly how reduced is reduced. Like, what does that mean? Instruction formats are simple and do not cross word boundaries. Now, when they say word boundaries, they just mean a fixed size, right? It's like, okay, the size of the instruction is fixed. Let me scroll down here.
I do specifically remember that part from your video, the idea that like an instruction always has to be the same length on ARM and RISC, and that's not the case with Intel.
Yes.
And x86, yeah.
And then we've got RISC branches avoid pipeline penalties, and that's sort of a thing that was true at that time. It's not going to be true now. It's talk about delayed branches, which are not a thing. So there's somebody's summary. It's Patterson, actually, who people would probably know. I believe they're, there's a computer architecture book, right? They're pretty that's a famous person, right? That's not just like some guy wrote a thing. And then contemporaneously at the time, I found this, which I thought was pretty good. It was basically a response to that paper that somebody else had written. And they complained and basically made the same kind of points that I would even make today. They basically complained like, look, I don't know what you're really talking about. When you say how complex the instruction set or reduce, that's like, what do you mean, right? It's a continuum. Like, we can have complex instructions. We can have not, we can have like a lot of instructions that do complicated things. We can not. How many of those should we have? Whatever. When you say like RISC, what do you actually mean? Is this RISC? Is this CISC? It's a continuum, right? There's no formal definition of those things. I don't know if you gave me an architecture, is that RISC? Is that CISC? Because you only had those 4 vague points. I don't know, right? And they go on to talk about like all of sort of the reasons why it's not so clear if this is an interesting way to look at chips, right? Even at that time. And I would say most of the things that they talked about back then are basically like the way it would boil down today. RISC and CISC are not that well defined. If you ask someone to tell you whether a particular chip was RISC or CISC, or the ISA was RISC or CISC, I'm really not sure how to make that determination. Sometimes there's very clear thing, like in that one of those points where it's like loads and stores cannot be part of other instructions. Okay, if that were the only criteria, then we could say that x64 is CISC and that ARM is RISC, because generally speaking, they do tend to follow those rules most of the time. Not exclusively, but most of the time, right? So that would be a difference. But all those other things that they were talking about, not necessarily so, right? And like the delayed branch stuff, totally not applicable today. And so I think this stuff ended up getting stuck kind of in our brains. People started talking about RISC and CISC as if this was sort of an important thing. But what actually happened when we get to the present day is, look, everybody now uses microarchitectures like the one I showed you. Instructions are turned into micro-ops, and the micro-ops are the things that actually do. Intel, does it have more instructions than everybody else, probably in x64? Yeah, I mean, it does, but it's like a very old architecture, and they've maintained a lot of backwards compatibility. And so they have a lot of those old instructions. Maybe a lot of them don't even get used anymore at all, but they're still in there, right? But if you look at something like RISC-V or ARM, what you will see now is they look a lot more complicated. A modern RISC-V chip looks a lot like an x64 chip, even in terms of its instruction set design. So let me show you that. Let's take a look, for example, if I can get down here to like the vector instruction sets, which are the things that do like the heavy lifting when you're doing computation. So if we go in here, we've got the V extension, which is the thing that a RISC-V chip has to use if it wants to be competitive for numerical computation, right? It's the thing that's going to actually allow it to do, scientific, math stuff, anything like that. Well, here's a section called Mapping of Vector Elements to Vector Register State. And it's going to describe here this thing called LMUL, which is state you can set in the processor as an instruction that says how you would like to combine various registers in the processor to larger or smaller registers, so that when you do operations, it will automatically happen on more registers than just the one you specified, right? Now, there's no way that you can tell me that that is RISC by any of our intuitive understanding of the word, like the way we've all been using it, where we're thinking like, oh, it should be like very simple. Like this is not going to be a complicated thing, right?
Yeah. Just the definition of reduce, this is the opposite of that. This is expanding the instructions by design.
And making them complicated, right? Like, oh, now all of my other instructions have to understand that this LMUL might be set so now this thing that used to only operate on one register is now operating on two of the registers, and so on and so forth, right? Now I'm making it sound more complicated than it is, because all of these things inside processors obviously are not the way that you think of them at this level. So, inside a processor, there's really no such thing as a register anyway. They're register names, and they have a thing called a register file that gets used as you use the names and all this other stuff. But my point is just, this ain't simple. If what you were doing is trying to write down the most straightforward, most basic version of something that did vector computation, it wouldn't look like this. It would never have this in there. So what is my point? My point is, all of these instruction sets are really doing the same thing at this point. They're trying to figure out what set of instructions compactly encodes what programmers are trying to do in a way that the chip can then execute quickly by quickly decoding and quickly turning into micro-ops that can then be quickly executed. That's what they're trying to do. And really, no one is thinking about CISC versus RISC, I don't think, anymore when they're designing this stuff. That's simply not a concern. Like, how complex it is isn't really the issue. It's more about how can I efficiently encode in these instruction encodings the things programmers want to do in ways that will execute quickly through this pipeline. That's all we're trying to do. When they started the CISC versus RISC sort of debate and doing that naming, they didn't have a model where microcode stuff was going to be free like that, where turning things into micro-ops was just part of what was happening. They were sort of thinking like, oh, with these RISC designs, we don't have to do any of that really, or we have to do very little of that. But really, nowadays, everyone does a ton of that. No one is really doing, on these bigger chips like the desktop, laptop chips, no one is doing those kind of really simplified versions where you wouldn't even have to microcode anything at all, right? And so I just kind of wanted to get that out there as sort of a second piece of this puzzle. RISC versus CISC, kind of like almost like a red herring. And I don't even think it really captures what hardware designers are doing anymore. I don't think they're really thinking about that. Does that make sense?
That absolutely makes sense. Like, this was a discussion in the 80s that led to two different paths being explored, but we've kind of landed in a similar spot down all of these paths. And calling one path red and one path blue doesn't really matter anymore because we've landed on purple anyways. Who cares?
That is a perfect summary, an absolutely perfect summary. And so with all of that background now, are there some differences between these ICEs in specifics that can matter, right? And I think there are. Things like loads and stores being separate, I don't think turned out to matter. I think you could easily design an ISA either way where loads and stores could be put together. I think that part of it isn't really all that relevant. So we're looking at those risk lists. Several of those things I don't think mattered very much. There is one thing that did matter, and that is the regularity of encoding the instruction. And this is the thing that you alluded to, like when I was talking, I guess in the stream with Prime. So one of the things that if we now kind of jump back a little bit and we look at these block diagrams, right? Let's bring up one of those Firestorm cores again. So one of the things that you'll notice up here is that the Firestorm core, again, this is the heavyweight core in a M series chip. What you can see is it has a lot of decoders here. So remember, we're getting instructions in, we're turning them into micro-ops. These decoders here, 8 of them, mean that on every clock cycle, right? Remember, this is a pipeline thing. We're going to do it. On every clock cycle, we can be expecting 8 new micro-ops to be feeding down the pipeline because they're percolating through here, instruction percolating through. It can get turned into 8 micro-ops. Now, why does this matter? Well, this is the instruction stream, right, that we're running. The fastest we could possibly run your instruction stream is obviously going to be limited by how fast we can decode it. If we can't decode the thing fast enough, then we obviously, it doesn't matter if we have a whole bunch of computation resources that could execute it. They don't know what to do. They're just sitting around waiting. So we have to make sure that this first part, this top part of the chip here, is fast enough that it is always going to feed the execution part. And this part becomes very easy on something like ARM because the instructions are a fixed size. So they can just throw down these simple decoders. They will decode the instruction. They know exactly where to start because each one of them just starts a fixed width away from the other one, right? And they all just go in parallel. And on every cycle, they can just do 8. They see a block of data coming in that represents the instruction stream. They decode it all in parallel, 8 at a time. Every cycle, 8, 8, 8, 8, 8. As a result, this part never has to worry about getting more work to do. It's always going to have a ton. Now, if we look back at the same diagram, again done by Cardiac here on the Zen 4, what do we see here? Complex decoder, complex decoder, complex decoder, right? See what I'm saying?
Yep, there's already a difference in the phrasing. It's called a complex decoder now.
Yes. This is much harder for them, right? When they have to decode something, they have to do a lot more work because they don't know exactly where the next instruction is. The reason for that is that Intel's encoding is a variable length instruction. Basically, it works sort of the same way. I mean, I guess, I don't know if people are, again, familiar with compression. This idea that, you read a byte in and it tells you whether like the next byte is going to be this or that, right? I'm looking at it. I'm like, oh, okay. If this byte's equal to this, then I know the next byte's this thing. That's what these have to do. Now, it's not really that big of a deal for them to do this. The problem is just knowing where to start the next one. Because if I want to do these in parallel, if I want to do 8 at a time, like the Mac is doing, right? Well, I don't actually know where to start the next one. If this guy knows he starts right where the program currently is, where the decode pointer currently is, this guy has to start somewhere after that, but he doesn't know where. So what they have to do is like these kind of complex, like guess based on bits feeding kinds of nuts to try and hope they get it right. And what they usually end up with are things that best case for most instructions will decode quickly, but also it decodes more slowly if it hits, other cases. And you'll also notice here, there's only 4 of them, right? So what that means, you can see actually multiplication here. And again, take these diagrams with a grain of salt. They're community made. They may be wrong. A Zen 4 engineer might be laughing at us right now because they know the truth and we don't, right? So I'm just telling you like
Yep.
an example that hopefully is correct, but I make no warrants of that. Let me see if I can flip between them. Yeah. What you can see here is the micro ops that are going out of here. There's one micro op coming from each of these decoders, basically, right? Per cycle, I believe is what it's trying to say there. So what that means is there's not going to be any bias as to whether or not we can get micro ops flowing through this pipeline. No matter what instructions you're doing, we'll be able, like, even if you have very simple instructions that could only produce one micro op each, we will still be able to do 8 of them because each one of these decoders is decoding a different instruction. By contrast, if we look at here, each one of these could be outputting 2 microops per cycle. That's a total of 8 microops, which sounds pretty good. Problem is, we only have 4 instructions to gather them from. So if those 4 instructions don't each code for 2 microops, we're actually not going to push 8 microops down the pipe, right? So we end up in a situation where we can't guarantee as many microops flowing through the pipeline because we simply can't afford the decoder logic to do it, or it's too hard to figure it out, or whatever, right? Does this make sense?
Yes. Can I see if this has clicked in my head to the point where other things I know are applicable? And I'm giving you more than ever at any point so far, full permission to be like, no, you're entirely off base. It's a problem for later.
Okay.
Is this why there is so much work for, I don't know what the terminology is, but the predictive modeling that exists in a lot of x86 chips, where based on the instructions, it tries to guess what next instructions are most likely, and it will fire different instructions that you might not have even encoded in case that is the next step, so that it has that ready if it is.
No, that is what we call speculative execution, and that is happening in all of these cores.
Okay.
Do you want to talk about that? Because we can definitely talk about that, but you could put it on the stack for later if you want.
Yeah, let's put that on the stack for later. I was just curious if like the reason for that being exciting and interesting on this side is because getting enough instructions through and enough microtasks through is challenging on this architecture. So having more is beneficial, but it sounds like that's not the case. It's just a thing they do.
That is a separate thing, and we could talk about that because it's actually for both of these. So the ARM cores have the exact same problem with speculative execution, and yeah, we could definitely talk about that. Let me just put button up this part because we're basically done with that. So again, because I'm not a hardware designer and I just don't have the information, I can't really tell you the kinds of stuff that goes on in here. But what you do hear fairly frequently is just that a lot of effort is put into this part of the x64 chips, trying to figure out how to decode more instructions at once. And that is something that is simply not the case on like Apple M series. So when they made that, I doubt anyone was sitting around sweating over how they were going to decode 8 things at once. It was more just like, well, how big is that going to be? Oh, it's going to be that big. Okay, we're done. Right? Like this was probably not anyone's thesis project going on over here, right? Whereas
to give
it
a real
absolutely
dumb
would have been on the other one.
To give a real dumb analogy quick, if we think of this, like, I always like to compare CPU architectures to kitchens because it's a very like real world understandable thing. Like cores are the number of chefs and whatnot. Here we can almost think of it as like this is an ingredient coming in that needs to be cut. We'll say it's bread. With this, the simple decoder, all the bread is always, every slice of bread is always the exact same length. You could even pre-slice it effectively, and it's coming through, and one slice is going down each of those. With the Intel version, with the x86, we now, a bread could theoretically be 2 slices wide or less, and now you have to know for each thing, like, how long is it, and make sure you cut it at the right spot.
It's basically like, you could be handed any loaf. Like you're handed some kind of French baguette, and then you're handed like an American sandwich bread, like Wonder Bread loaf, and you just have no idea what's coming in, right? So you're just sliced, it's just a complete nightmare. Whereas the other one's like completely regular. It's always this exact loaf, and you made a little machine that just has the 8 blades spaced out, right? And you just go whomp, right?
Yep.
And so that part, I think, really does matter to some degree. Like that is a thing that you could actually point to and go, this is creating a problem. And I'm pretty sure x64 engineers could do more, have done more earlier if that hadn't have been a problem. Now, again, I wish they were here to tell us if that was true or not, but that's something I would point out where it's not a lie that ARM kind of has a leg up there a little bit.
But to compare it to like To compare to my video, though, where I said like this matters throughout the whole diagram effectively, you've isolated where this matters. If you like zoom out in the diagram a bit really quick, it's literally only the orange section where this like matters right now, where it's easy to or misassume, which I did, that much more of this diagram is relevant in this conversation.
Exactly. It's like, this is the part where ARM matters for the most part, and might have an advantage long term, right? Where it's like, at the limit, you may really not want variable instruction encoding. Or another thing that's very possible is you do want variable length instruction encoding, but you want to do it in a smarter way, like some way that was more designed for batch decode. Because remember, they were not thinking about this when the x86 and then x64 instruction sets were designed. They really weren't thinking about, oh, we're going to want to be decoding 8 instructions at every cycle, right? That's not what they were thinking. So, there's that. Now, are there some other things? There are, actually. One of the things that Intel has that ARM doesn't have, that also, could be said that ARM might have an advantage here. Intel has a more strict memory ordering. So the rules when a CPU core is like writing stuff, the rules for how that becomes visible, or when it's reading things and some other CPU core may have changed those things or whatever, right? Those rules are stricter on Intel than they are on ARM. ARM has a more relaxed, called memory ordering, or memory ordering model, or just memory model. So technically, it is a little bit more difficult potentially or difficult might be the wrong word. It may cost more in terms of performance to ensure that memory model. And so it's unclear whether that could also be a factor going forward. Like, I'm not prepared to say certainly, and I haven't seen anyone really do a definitive breakdown of this, but I want to say that people did test on the M series and figured out that there might be like a 9% performance gain from not having to use that model, which brings me to something you mentioned in the video. So in the video, you said something about, and we actually mentioned it, thing I said it would come back later. You were saying the M series puts stuff in the chip for Rosetta, right?
Yes.
That's one of them. M series chips apparently can switch their memory model. So normal ARM chips only have the ARM memory model, which is that relaxed memory model. The M series chip has both memory models. It can use an ARM memory model, or it can switch to the Intel memory model. Why did they do this? Because this is one of the very expensive parts of emulating x86 on ARM. So this was a part of the video that you were talking about, where you're talking about difficulties of x86 emulating on ARM. And like, I think that was kind of off in the weeds, because you at that point been talking about like divides or something, and it doesn't have a divide, so I have to emulate it. That's not the problem. The problem are these very hard to really emulate things of like, what order will multiprocessor things see stuff in? It's like, well, how am I going to emulate this more strict memory model on a processor that doesn't do it? I'd have to put in like some extra mutexing or something, right? Or extra fences or things like that become really heavyweight. Whereas if the CPU itself is just guaranteeing that, well, then it's no problem, right? And so if you look at the actual things that they added to the M series to support Rosetta, it has nothing to do with things like divide, because they already have divides and all that kind of stuff. It's a very powerful chip. But some of the things they needed to do was stuff like emulate the memory model, right? They can get a lot better performance if the CPU could do that natively. I want to say like Snapdragon can't, and it is a costly part of the emulation. Don't quote me on that though, because I don't really know much about those new Snapdragon x86 machines. Another one is sort of this idea of flags registers, which I don't want to open up a whole can of worms there. We could go through it. I don't know how long you want the stream to be, 17 hours later. But there's sort of this idea when you do operations, there are these things in the operations that get tracked. So for example, if I was to add 2 numbers together and the result doesn't fit. So I add 2 32-bit numbers together and the result doesn't fit. So there'd be a 33rd bit that should get set. That goes into something called a carry flag, which is this sort of state that the processor tracks, right? And you can then do operations that are dependent on that. You can branch, for example, on whether or not, a carry flag is set or something like that. I'm just giving hypotheticals here. Those are things that you could design a processor. Well, the Intel set of flags and when they're tracked and what they mean are different from what the ARM ones are. And I believe, in fact, let me look. I pulled a resource because I remembered you talked about this in the video, and it's not something that I have really studied. But this guy, Douglas Johnson, I think is his name. Dougal Johnson. Dougal Johnson posted this really nice reverse engineering here where he was looking at what stuff they actually had, right? And it turned out that they added some stuff to make those flags work like they do in Intel, again, so that you wouldn't have to do so many heavyweight operations during emulation to like track these flag operations. The CPU would just remember the flags the same way Intel does, right? Here's that memory model thing. Yeah.
Yeah. And what's Apple's secret extension I saw at the end there?
Apple's secret extension, I think, is just more flags handling.
Makes sense.
So they're just, again, because otherwise you'd have to do some arithmetic to compute these flags yourself in order to like do the proper dependent operations. And so again, if the hardware just does it, it's way easier to do it that way. My assumption, and I could be very wrong about this, would be that Apple probably at some point will just pull these out. Like once nobody cares about running old x64 stuff, then they probably wouldn't. Like they'll probably just rip this out of the microarchitecture,
so
right?
It's my understanding that this is still in the architecture for things like the iPad CPUs that are M series CPUs. So their manufacturing isn't being more considerate yet. But I absolutely do see a future where that's the case, or they move to like higher level software emulation of these features because the chips are so fast. And if you're running an old Intel program, like you're used to it running a certain speed. But like I managed to go, I think, about a year without. Rosetta also requires a program to be installed. So I went a long time without that. Actually, can you go back to this? Because there was one other thing in there I wanted to call out. Sorry for making you go back. But,
no problem. Where was it?
It was right after the like Apple's secret thing. There was a little like part near the end there that I wanted to call out because it touched on something else. Yeah, it's visible there. So before we get to that though, I lost my tangent. It's fine. There was another piece here that I thought was really interesting that touches on what we were discussing before, which is the throughput bound nature of the chips. It's said in here, actually it might have been slightly further down. There was a line here. Here it is. Yes.
To avoid being throughput bound?
Yes. Which I thought was really interesting, touching on like what we were talking before with like the instructions and how they're being parsed and pushed through. Historically, we've had to worry about the actual throughput that can get to the actual chips doing the compute on our processors. And Apple's architecture is one of the first powerful CPU architectures where that just kind of can't happen.
I mean, one of the things that they did, and I mean, it's pretty good that they did it too, because it kind of makes everyone have to, they kind of rise the tide, right? And all the boats have to come up with it. But they basically said, look, we're just going to go all out. Like, we're going to make a big chip, and we're going to put a lot of stuff on it, and we're going to have 8 decoders, and that's just how it's going to go. And we're going to have tons of ALUs, and we're going to have, our execution units and all that stuff. And we're going to make really deep pipelines for everything, and really big register file. Like, everything's going to be big so that it's like massive in terms of like how much work it tries to get done every cycle. No, part of the chip will become a limiter. And it worked. Right, for single threaded code, which is where you care about this sort of stuff, it does those Firestorm cores. They do an absolutely great job because everything is very big, right?
Yeah, my iPad outperforms even the best desktop chips in single threaded, which is just unbelievable that Apple's pushed that hard. And I just think it's really cool. Somebody reminded me in chat what I was talking about before was downloading Rosetta. Rosetta also requires a software component on your machine for it to work. And it doesn't come by default in macOS. You have to install it when you use a program that requires the backwards compatibility. And I've made it years at a time without installing that. And it's like very niche audio software that I use that requires it. Like, I'm a big fan of Isotope for audio stuff, and that's the only time I've installed Rosetta for like 3 to 4 years now. So your point that most people don't need this and are moving away from it is entirely true. I would argue a lot of why the effort went into Rosetta in the first place was that Apple wasn't sure how quick the adoption to Apple Silicon would be, and how quick the adoption for software developers to start compiling to native Apple Silicon was unsure at the time. And they wanted to make sure there was a happy path for people to use these new machines with the old stuff. No one expected the massive size of the performance win that we got with Apple Silicon. And if they had known about all of that, they might not have even bothered with Rosetta in the first place. And now it's just kind of there because it's there.
Well, I'm sure they needed it for exactly the reason you're talking. Like, you don't want all those unhappy customers. And like I said, I'm sure my assumption is they will just tear this out of the architecture at some point, right? So you put it in for some number of years, and then when there's no one is still running an old version of Isotope, right? When it's like basically nobody, then you pull it out. And that seems like, I don't think it's taking up a huge amount of you know.
Chat made a really good point. Gaming's a really good reason for them to keep this, because they're trying to push gaming on Mac harder right now, and all of that relies on a lot of these things.
Oh, okay, yeah. Yep. Well, if they want to do that, then yes, sure. But I was kind of assuming, because game developers don't compile for Mac. That's true.
Yep. Now that I've remembered that point, I'm going to walk back everything I just said. Rosetta 2 is here to stay because Apple. It fits Apple's half investment into gaming perfectly, where they won't do things specifically for it, but they won't remove things that make it possible.
Okay, so you think they're gonna ride that fence all the way down? Okay.
Apple is very good at riding fences when they're not willing to commit to a customer base.
Okay. Yeah. Well, anyway, though, back to the CPU architecture stuff. So that's what's in there. It's basically, again, microarchitecture wise, it's just saying, look, we have all these different things. The way these execution units work, it isn't always that expensive for us to just add in some parameters to them. Like, look, the flag gets set this way on Intel. It gets set that way on ARM. Can we handle both of those? Yeah, that doesn't cost us very much, so we just did. And now it becomes a lot easier for us to do this emulation, and people have a better experience with our thing than they would have if it was kind of jankier and slower and, all that sort of stuff. The memory ordering one, again, being a huge one. I don't know how expensive that was for them to do. But pulling it back to the ISIS thing, I wanted to mention that one only because memory ordering is different from the ISIS and can make a difference in performance potentially, because it could be the case that the cores cannot achieve as good a performance for a particular die size or a particular clock rate or whatever else you want to look at if you have to do the stricter Intel memory ordering versus the weaker ARM ordering. And like I said, there are some examples of people who have done benchmarking on M-series chips turning that memory model on and off, because it's one of the only chips we have that can do two different memory models like that. That's a performant chip. That's like a high-end chip we can test on. And they did say there was something like, I think it was 9% performance difference between the two. That would be an important thing. However, of course, we don't know if that's actually representative, because it could just be that it's 9% slower because it's Apple's less preferred path. So it's kind of more jankily implemented in there. And they could have, if they had done Intel's memory model, they could have done it just as fast. I don't know. I really don't know. But you would think that, it would be something where if it is 9% slower, there's more stuff going on there. Maybe that's indicative that ARM's memory model long-term is a better choice and will lead to slightly faster or slightly more efficient power-wise or whatever metric you want to optimize for, because they don't have to do that. I couldn't say. Hardware designers probably have an opinion on that, and they probably won't say either.
Yeah, I could tangent way too long into memory, and I will say many much dumber things than I said in my last video if I do. Okay. I have been to hell and back with weird memory isolation things on Windows, and just like the different like hypervisor layers that exist now for doing like emulation, and how they're using those to try and make applications not have access to each other's memory and shit. It's terrifying. So for the sake of my audience and my own how people view me generally talking about things I know what I'm saying, I'm going to shut the hell up and let's get back to architecture. Okay.
Totally fair. So I feel like we've covered a lot of the things that were in that video now, just based on like what I had taken notes on. And I guess before we just go into any general questions, there was really only one other thing that I guess I would uh, wrap up with, which is the point of your video in the first place. You were actually looking at an article that was like x86-64 team up with
Mhm.
Intel and AMD. They're going to create this consortium and work more closely together, right? And one of the things that you point out in that article was talking about like AMD's like supervisor entry extensions was mentioned in there, and like Intel's Fred, the thing, and that kind of stuff. It's like, what the heck is this? Why are they doing this? What's going on? And I just wanted to touch on that a little bit because it's also a little bit interesting to talk about that. Although it's it's actually pretty boring stuff. After I think the microarchitecture is more interesting, but I just pointed out. So where a lot of the stuff comes from is not really like, oh, like we kind of talked about the risk versus CISC, or does this thing have a divide, and like all that stuff. Really, what they're talking about with these kind of consortiums and moving x86 forward, it really isn't all that stuff. What it is are certain easily identifiable pieces of the ISA that's just like, look, we could do this better. Just generally, it has nothing to do with any, risk versus CISC or anything like that, or reduction even. It's just the way this was done at some point in x86's history was not great, and we can revise it now. The thing with like the AMD supervisor extensions or Intel Fred, they're both trying to fix the same thing, which is how like interrupts are handled during like a syscall or things like this, how the interrupt descriptor tables laid out. Nothing to do with like ISA stuff, really. It's just, hey, we need some rules about how these calls work, what the calls should be exactly. We need to make sure that the rules for how the chip does the interrupts fine. AMD and Intel both want to fix this. If AMD introduces one and Intel introduces one and they're different, now it's like, okay, now the Windows kernel team has to implement one for each of the different OS vendors, and the Linux people have to do one for each of the, right? And that doesn't really help anybody. So that's one thing that they were talking about. It's just like, look, when we need to fix something like how the interrupts are going to work when we do a syscall, or if there's an interrupt during a syscall, or how we restore the interrupts, or blah blah blah. Let's just make a good one that's not crappy like the old one that doesn't have the problems going. We'll just make one and we'll agree on it and we'll go for it. That's one thing they're trying to do. The other thing is some aspects of Intel architecture are actually just kind of bad for like designing the chips. They're just things that don't need to be there that can be removed. It has nothing to do with the instructions so much as how they were defined to operate. So, for example, Intel, for some reason, and I'm sure they had a good reason. If I had not been 3 years old or something when the x86 comes out, maybe I would have been able to tell you. But back then, when they defined like a shift, like I'm going to shift bits in a value left or right, they defined shifts to, if you shift a bit out the top, it like goes into the carry and things like that. Like the flags get modified by bits that get shifted out and other stuff like this. There's weird things that happen in shifts in terms of affecting flags. Processors today still have to track that. So when they're doing things like shifts, they have to like update the flags and stuff like that, which creates these dependencies because they don't know if someone later is going to look at that flag. So it creates a dependency where one probably shouldn't have existed before, which creates problems for scheduling, the blah, blah, blah. There's a bunch of other minutia like that, where it's like, look, nobody wanted this anymore. Look, we don't need this anymore. Just get rid of it. Make a shift instruction that doesn't affect the flags at all. And then every time a compiler goes to output a shift, it's going to use that new one, because it almost never actually wanted to affect the flags, because it was never going to do anything with that information in the future.
Yeah. It's an unintended side effect, effectively.
It's basically something that creates a potential future dependency, so the CPU has to handle it, but no one ever uses that future dependency. So it's just creating work for the CPU and potentially preventing optimizations in there that really, nobody's taking advantage of. So just get rid of it. So there's a bunch of stuff like that, right? Where they're just like, let's streamline these things, and everyone knows these are wrong. Let's just fix them and move forward. So a lot of stuff is like that kind of stuff. And I believe the consortium is just trying to do that in a more organized way, assuming Intel survives long enough.
And none
But
of this is part of like the x86 standard or instruction set. This is just details of how Intel has implemented it that cause things to be less than optimal and for weird complexity across different like architectures and like software that runs on them.
well, it is part of the standard though, and that's sort of what they need to fix
Okay.
because it says in there, it's like, hey, this is the shift instruction, and it's going to modify the flag this way. So that's all. Like you've got to do it, right? And
So
so
do AMD
and
processors
Intel
do that
both
as
have
well
to do
then?
it. Sorry.
So AMD processors also do that.
Exactly. They have to, because otherwise the software wouldn't work properly in the rare cases where someone actually uses that flag, right?
Okay.
And so they're just going to introduce, they'll just say, here's a new instruction that doesn't affect the flag. So now all the compilers will output that and we'll be good, right? And they can also do things like trying to more regularize the instruction encodings, so to make those decoders a little simpler. All of that stuff is stuff they can do with that consortium. And it's all stuff that does need to be done to x86-64. Again, not because of CISC versus RISC or any of these other things, or even the number of instructions there are, more just because it's a legacy architecture. It's had to maintain backwards compatibility for a tremendously long time. And some of the things that are in there can be redone to be better now. Just we know more about what people are trying to do in microarchitectures. We know more about how, like you said, I think you said there's a red and a blue path and we ended up at purple. We know what purple is now. So we can make some better choices with how this ISA is laid out that will make it more competitive long term. And I believe that's like what they're trying to do, hopefully, right? So
makes a ton of sense. Also, like having Microsoft on that group is essential for making sure these things actually end up benefiting how most people are consuming the stuff, which is on Windows computers. Also, having people like John Carmack in there is essential because he understands how games work and are optimized in graphics programming better than almost anybody ever. And having people like that to make sure these decisions don't have weird side effects, like in terms of the software that we're writing, but also are actually helping make the standard better. Makes a ton of sense.
Yes. And so there's reasons to be optimistic about that. And who knows what will come of it. But even, even before they announced that, they have some things like that thing about the shift I was talking about was something that was proposed by Intel, I don't know, 2 or 3 years ago or something like that. So it was already in the work. Like Intel was already doing some of this internally. They were thinking about this and proposing these sorts of things. And so, hopefully this consortium can be a way to sort of get those things through as quickly as possible, whether they come from AMD or Intel. This was stuff that was being done because people know the ISA needs to get some improvements in certain places. So, yeah.
Makes a ton of sense. I also really hope Intel doesn't die, as somebody who invested a lot of money in them earlier this year, because I don't think they can die. Fingers crossed. This is not investor advice. This is my own bad decisions.
It would be bad if they died. I am hoping that they pull it through, but obviously they're in a pretty bad state currently. So, but
yeah,
we don't really want to go down to one x64 provider. But yeah.
On the topic of speculation, do you think we can talk a bit about how the speculation stuff works? This is something I clearly don't understand at all that I think is really cool, and if you only if you have the time, of course. I don't want to keep you for too long if you need to run for anything.
No, I mean, like I said, I love talking about this stuff. My only regret is always that I just don't know more. But like I said, like I feel like I wish I could know like more of the specifics because, and as I've said many times, you've heard me say, I just don't know, right? And that's the truth. I really don't.
I don't think it's fair to call it a regret if your hands are tied. Like you can't do anything about it. Like if you could know more, you would. This information isn't there for you to have.
I could go work at one of the companies, right? But then I wouldn't be able to talk to anybody about it.
Yep. So yeah, you've done nothing wrong here. You can't regret something you don't have a better option for.
So I'll go back to an official slide, right? So this is the AMD official slide of their Zen 4 chip, Zen 4 core. So what is speculative execution? Well, if you recall back to the chat questioner who asked, like, what is a cycle? And I was saying, like, well, who couldn't tell you electrically why, but things in the CPU have to happen in these small steps that are coordinated. So the time that it will take you from start to finish to execute a particular thing you want to do, like just something even as simple as adding two numbers together, as we've talked about before, the very most simple thing you might want to do will still take on the order of like 14 of those clock cycles to complete, from the time that it is fetched and decoded and put into a queue and scheduled and ends up at a like an actual logic unit, and then gets retired and blah 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 blah, right? Like all of these stages that have to happen. And so when you think about that, you end up in the exact same situation as the analogy I gave with the data center. You can't wait for something to complete. You can't wait, get one byte to come all the way back and then ask for the next byte, right? You are just dead at that point. You have to be doing things in this sort of in like a stream, right? It's constantly sending me the bytes and I'm constantly sending back new requests, and those things are crossing in the night, right? So the way that CPUs try to get more performance out of these same instruction streams is because they fundamentally have this limit of it's going to take 14 cycles or something to get a single thing done. So they know they can't wait 14 cycles to do the next one. That would be the world's slowest chip. To put it in perspective, I mean, I don't know, but you could argue that would be something like 50 or 60 times slower than a current. Like, I don't know, it'd be a crazy amount of speed slower if it had to do that kind of waiting. It's just you would never want to use that. So they need to go faster than that. And so what they do is, again, coming back to this diagram, they end up breaking this up into pieces where we decode, we create micro-ops. Those micro-ops go into a pipeline. The pipeline has these things called schedulers, which are basically like queues that hold things until they're ready to be executed, and then they are executed, right? Now, as I'm saying this, you have to remember, like, okay, well, if you think about that, I gave you an instruction that was like, I want you to add these two numbers together. And that means that has to flow through this pipeline the entire time without us ever even knowing what the two numbers are, right? Because I have to decode the thing without knowing what the two numbers are, because they potentially haven't been produced yet, right? Remember, I'm trying to do all these things without waiting for the other things to occur, without waiting for the instructions that came before me to occur. So I need to be able to do that. I don't know what the two numbers are. I just know it's an add. That got produced. So we get into something like this integer rename here, right? That's literally what like these two rename boxes are doing, are like trying to remember who said they were going to do what to what. So the add that said you're going to add this with this, those two things that add A and B, we're going to like track what the A and B were in this box. We don't know what they are yet because no one's even potentially produced those numbers. The add then goes into one of these schedulers, and it's going to sit there for a little while until someone actually finishes producing the A and the B, right? When the A and the B are actually ready, so my add can occur, then the thing can grab those values out of the register file that's actually storing values that other instructions are producing. It can then flow into one of these ALUs that can do an add, do the add, and then feed back into like the register file again, right? Where it can be written back for another thing, which will trigger other things to be ready. Okay, now that's a very quick thing that leaves out a ton of stuff, but it's the only thing you really need to understand for speculative execution. Just even that, which leaves out a ton of details, lets you know something, right? When I came through here and stuffed these things in the queue, what did I say? I don't know what the numbers are. And hopefully you can see why that is. I had to start the decoding before any of the other instructions that were in front of me that produced these values, right? I mean, maybe I should make this even more concrete, just so it's not abstract. Literally, if I said something like, okay, I'm going to do A equals, B, or just like 1 plus num. And then, actually, let me take two things in here. So I'm going to take A and B. I'm going to multiply those together. I'll use an add because we've been talking about add, right? And then I want to take that and I'm going to multiply. I'm going to square it, right? So I'm going to take A plus B in, and then I'm going to square it, right, to produce D. And then I'm going to return D. So this entire thing, incredibly simple. It takes two numbers, adds them together, and then squares the result. That's it. Simple. No big deal, right? So think about what I'm saying. Just this incredibly simple thing. It's literally just an add and then a multiply. That's it. Well, when that's flowing through this pipeline, the add and the multiply, they're coming through here. The add is getting decoded. The multiply is going to get decoded long before the add has ever hit these execution units, right? Because they're pipeline. They got to flow together. 14 cycles potentially to finish that add from start to finish. It's too long. So they all have to flow through here. I got to get everything down here to be ready to go, right? So the add flows through, it's sitting in here. The multiply flows through, it's sitting in here. So I don't know, right, the numbers for either of them. Eventually, the add becomes ready. I do it. Eventually, that completes. The multiply can now happen. It completes, right? So does that make sense? At least
Yes.
it's a vague sense, right?
Yeah.
Now assume I have an if statement.
This
Right?
just made it click.
I need to check something, right? I don't know what was passed in, but I want to know if it's going to be positive. And if it was, I'm going to flip the sign of D. Just who knows, right? Just something like that. So the problem that I have now is I've got a conditional. I don't know whether I'm going to do this. I have no idea. Because remember, all of this stuff, all of the micro ops are probably going to flow through this pipeline before we've even done the add, right? Let alone the check to see, because that's going to be another micro op, the check to see whether it's greater than 0 that we have to branch on. Now, I guess technically it's not going to be another micro op because this actually affects the flags. Sorry, pretend I didn't say that. We're not going to have done this add by the time that we actually need to be decoding these micro ops. So the micro op that's for this negation, right? We will be decoding this long before we have done this A plus B. So stuff flowing through this pipeline, we now have a problem. Which micro ops do I send down? Do I send down the D equals negative D micro op, or do I not? I don't know which way this branch will go until much later, so what do I do? Does this make sense as a dilemma so far? Right? I'm working ahead. This is where speculative execution comes in. The way these chips work is they guess. They make a best guess about whether or not they think this branch will be taken or not, right? Whether they think they will come in here and do this or whether they won't. This part of the chip, right, contains a thing called a branch predictor. It's right here in this box. And what that branch predictor's only job is, really, is to try to guess what instruction will be executed next, right? So as I'm feeding this instruction stream through, it's all hunky-dory. We're decoding them all. And again, this has nothing to do with Intel, or the ARM chip has to do the exact same thing. So that M series has got those 8 decoders. They're running gangbusters, 8 simple decodes every clock cycle. We're loving it. All of a sudden we get to a branch. Crap. What do we do? Do we go to the target of the branch and start decoding those instructions? Or do we skip the branch, figuring it's not going to be taken, and decode the other instructions that we would have done, right? Put into phrases here, do we tell the decoders to decode this and feed that through, or do we skip it and just tell it to decode this? Which are we going to do, right? The branch predictor's job is to guess. It will simply guess, and then whatever the guess is, that's what will be done. The reason that we call this speculative execution is because it may not be true. It was based on a guess, and that guess could be false. So what happens at the end of this pipeline, and it's kind of not really shown in here, there's this thing called a retirement buffer or a reorder buffer. There's some different phrases for it, but it's a larger instruction retire queue here and so on. So retirement, reorder buffer, whatever they want to call it, there's a thing which basically retires the actual effects of instructions. So they kind of go into this like serial queue at the end where they're just getting sort of like their effects. If they were going to write something permanently, those get sort of retired, as it's called, meaning we consider them finished. And what that will do is when it gets to here in that buffer, it will look to see whether what it guessed in the branch predictor is what the value actually was. So if the branch predictor guessed that C was going to be greater than 0, it's not really what the branch predictor guesses. The branch predictor just guesses where you're going. But for purposes of this explanation, if the branch predictor had the guess that C would be greater than 0, right? But when we get here, it turns out that it wasn't greater than 0. That's like a misprediction. And at that point, what the retirement buffer will do is it has to flush the pipeline of all the micro-ops that were decoded in between here and then, flush them all out of the pipeline, and start over. And that's what we call a branch misprediction penalty. It's the extra cost that you pay because all of those micro-ops that were in flight, that we had stuffed into these schedulers and that were ready to go, oops, it turns out they're the wrong micro-ops. We got to flush them out, and we got to start over. That time it takes for this thing to spin back up at a new location, pump enough things into this scheduler and get it going again, that is your branch misprediction penalty. And that is why mispredicted branches cost so much more than a branch that's predicted properly. A branch predicted properly is basically free. A mispredicted branch, very costly, right? Does that make sense?
Yes, this makes a ton of sense.
Okay, so speculative execution. It's called speculative execution because it's exactly that. It is speculating that you are going to want to do these operations. That may not be true. The reason you get things like, side channel attacks and stuff like that is because there's a lot of these speculative things happening on the chip. And sometimes they have, as it turns out, observable effects that you really didn't want to have happen. Spectre and meltdown, those sorts of things, right? The CPU is requesting memory sometimes speculatively. It's doing this branch prediction stuff. That's all speculative, right? All of these speculative things it might be doing. Some of those have observables. Those observables can be very bad for security because based on, looking at the statistics of timing of things that go on, an attacker can observe some of these things that happened, potentially at a higher privilege level, like where you're going to actually be executing in the kernel or something like that. So having access to things it shouldn't have access to by observing certain timing characteristics of cache probing or of how long something takes to execute, who knows what, they can then see some of these speculative execution things that have happened. They can do things which will allow them to leak, information to leak out. And that's why you get that sort of stuff. So those are two things with speculative execution. One is just, hey, this happens all the time. You get branch prediction penalties because of that sort of thing. That's speculative execution. We also have this sort of other concept, which is side channel attacks, which is when you get these speculative executions that can have their effects actually observed. So even though that retirement buffer is trying very hard to make it look like those speculative things never happened, they actually did.
This is super informative for me and helps clear up a bunch of misconceptions I had. I was under the impression that part of the branch prediction is it would try to run multiple potential branches, and then the one that's correct is the one it would resolve. The fact that it just guesses one that it thinks is most likely and then walks back if it's wrong fundamentally changes my understanding of this, and I'm very thankful I have this correction.
That is what it does. Yes, it only really does one. I don't think there's been a CPU, at least not a mainstream CPU that I've ever heard of, that tries to do both sides, because what they've mostly focused on is just trying to get that branch predictor really, really good, right? And they keep trying to make those improvements to the branch predictor so that it's wrong very infrequently. And I would also add that speculative execution, that retirement buffer, the way I said that maybe made it sound this way, and I don't want to leave that impression. Speculative execution things, it's not even just that they're sitting in here. They may have executed. Because in an out-of-order CPU, it can execute anything that's ready to go. So if it saw that it could do this negation early, like immediately after this was computed, but before it had looked at this, it could issue it. It may have already computed the results from these things, and those are just sitting there waiting in that retirement buffer. So it's not even pending micro-ops. It's like completed micro-ops that have to get flushed, right? So
that makes sense. The only immediate question I have here is it possible as a developer to indicate to the processor what branch you think is most likely?
So it used to be like branch prediction hints were like a more common thing in the olden times. I want to say that that's really just
But
fallen out of favor. I feel
what
like
would be considered olden
nowadays,
times? Like how long ago?
15 years,
Damn.
10 years. I don't know. That's a tough one because I don't really remember off the top of my head. What I will say is what you are talking about existed for sure. Branch prediction hints are 100% a thing, and they still exist today. So it is 100% a thing. In terms of what these architectures expect to get out of branch prediction hints, my understanding is very little now. So I think it's pretty much all just about these really good predictors, and they just don't branch prediction hints. I don't hear those mentioned hardly at all anymore. So I think nowadays they've just gotten the predictors good enough that it's not worth it. Like anything that you could have told it at runtime, it figures out basically immediately. So it's really, they're so far past that now that they're looking at things that you wouldn't even know how to hint, right?
Mm-hmm.
They're looking at things that are like pattern based. So like based on the data that's flowing through it, it just detects like, oh, this happens to be like 2 taken, 1 not taken pattern. So we did it, right? Or whatever. So they're pretty sophisticated now. And so hints, I think, are kind of fell by the wayside when they got good enough.
Chat, I hope you guys know how hard it is for me to not go on a tangent about React compiler and how it's the exact same thing right now, but it is, and this hurts. Quick TLDR, React's trying to get more efficient. One of the key things to making React code more efficient is memoizing things so that React knows it doesn't have to check it over and over again, and memoizing everything from a component to a function, whatnot. Historically, we've written those memoizations ourselves when things start to get slow. The React compiler auto-memoizes everything by creating a graph of like the variables and where they're being passed and where they're being instantiated. So everything is memoized, but it is predictive and it's doing its best. And you could still write these use memo calls yourself. We've had to, our entire careers, tell React whether or not something should be updated or not. And by default, it just updates. Now we have to unlearn that. We have to stop putting the hints into our React code because in reality, it makes our code worse to have these additional things that we shouldn't have to think about. It is additional complexity in the logic that we are managing and we are building that the system can do itself. And the system, not only can it do it as well as we can, it often can do it better because it will notice things we never would have. And it allows our code to be simpler, and simpler code is often easier for these architectures to parse or process.
And I would assume, although I obviously don't know anything about that specifically, I would assume that the same aspect is at play here, which is that fundamentally the data is dynamic a lot of the times. So it, at runtime, the CPU, or in this case, the memoizer, has more information than the programmer does because the programmer doesn't know exactly what data it's going to get, they're going to get fed at the time. The CPU does. It's seeing the actual branch pattern, much like the React memoizer presumably is seeing the actual usage pattern that's flowing through it at the time. So technically, if it gets good enough, it should be able to be better than you are because it has the data and you don't, right?
Yep.
And that is, I believe, I'm pretty sure that a hardware architect would say that that is where they are today on these high performance CPUs. Their branch predictors tend to be significantly better than what you would get if you just were using a hint.
Exactly. And it's weird how similar this is. One of the cool things with the React compiler is they have a tool similar to what you were showing us with Godbolt, where you can put in React code and it spits out the React compiled code. And they have some special flags now where they can inline a variable so they have access to it later, depending on how you passed it. And it looks like something you'd never want to write, but at the very least, you can read through it line by line and see those optimizations and see the predictions it is making, which sadly we can't do here. There's no way for us to see or at least trivially, given some C code, what path does it think is most likely. At least we get that in the JavaScript world, which I think is really cool. And it's helping me a ton with understanding this stuff and the value of it. Again, this theme of us web devs and software devs, especially application world devs, our dependencies need to, at the very least, understand these things to make more efficient software and to give us better building blocks. More than ever, I think being a web dev that understands these things is a potential huge value add to the entire web world.
Yeah, Absolutely. And I mean, actually, believe it or not, we can sort of, even at the microarchitecture level, we are allowed to get some observations about the branch mispredictions. There are actually counters you can read on the chip that tell you how many correctly predicted, well, how many branches and how many mispredicted branches there have been between any 2 points in an execution path. So one of the things we actually do is look to see how well is the branch predictor predicting this particular thing, which is pretty fascinating in and of itself, right? For
That
study.
is super cool. And somebody mentioned in chat that Godbolt actually does have a way to visualize this too, which is super cool. That tool seems unbelievable.
To visualize what?
The different loops and predictions that will be made. They didn't give specifics, but someone said that Godbolt is able to show this.
I'm not sure what it would show though, because the predictions are based on data, so you wouldn't really know, right? So I'm not sure. I don't know about that, but maybe. I mean, one of the things is it does have a number of tools in here.
Oh, branch rankings. It lets you visualize apparently.
Okay, because it's got a it also has, where is it? LLVM MCA, which lets you see basically like what the code will run as apart from the branching. That's the thing that's built into LLVM. But
that's
yeah,
super cool.
Actually knowing how the branches got predicted, you can really only do at runtime by reading the counters. And it changes per CPU too. So
yeah, this is super cool stuff. Is there anything else specific that I got wrong that's worth covering, or do you want to dive into Q&A quick?
I'm happy to dive into Q&A quick. I think we literally covered just about everything. I'm assuming there's not a need to cover. I think at one point you had talked about Apple adding video handling on their chip, and x64 side not having thought about that as an option. We could address that part obviously, but I don't know how useful it is.
Yeah, I know I was somewhat wrong on that. I believe Apple was one of the first companies to like push it really hard to have like video encode specific hardware on CPUs, but if that's wrong enough, we can dive in.
So yeah, I mean, maybe we should just cover that really quick then.
Let's do it.
So I think it's important, because I wanted to draw a distinction there, because it's important to remember that an M series chip is not a CPU. It's actually like what we would more commonly call today an APU, which means it has the CPU and the GPU together, all on one die. It's like it's got multiple sort of processors, smushed together.
Yep.
In fact, we have? I don't know if I have an M series die shot.
Quick clarification. I hear SoC being used a lot more now. Is like SoC like even higher level than an APU? Because I was understanding of APU is CPU plus GPU. SoC is APU or GPU, CPU plus other things like memory.
So I share your confusion. So an APU, I think we just use anytime we're talking about the fact that there's a CPU and a GPU on the same die. And SoC is, usually like a broader term that can encompass potentially more things than that. But I guess I don't know if it has a textbook definition. So I just meant the M series chip is kind of an all-in-one processor cluster, right? However you want to think about that. Whereas if you were to think about just like a Zen 4 core or a cluster or a CCD on a Zen 4 die, that's just the processing part for a desktop chip that's going to have like a GPU plugged in as a discrete card, that's like a very different thing. So I was just trying to make a distinction between those two things. I don't know if system on a chip really has a hard definition, right? It's used in a lot of ways, I think.
Yeah. I've only ever heard APU in the context of AMD as like a marketing term. So
okay.
Yeah, I was under the impression like SoC is the more generic term for this, and APU is like an AMD thing. Somebody in chat said the same.
I'll stay away from the terminology entirely, because like I said, I don't know how they want to define those things. But so like if you were to look at an M series die shot, so this is the actual chip, right? From AnandTech's labeling, because again, if you remember, you don't like hardware companies do not give you a labeled die shot. Forget it. You're never getting that, right? You might get a die shot. It might not even be accurate. It might be a fake artistic rendering die shot, right? But they're not going to label it. So here is the one that Anantech labeled, and you can kind of see this is when you talk about I'm going to have like I think this is an M1. And if you look at how it's laid out here, you can see that each one of these little tiles here is like one of the GPU processors, right? So it's like these are GPU cores here. And this is like going to be like a backbone, probably like a memory thing with a cache, I would guess. I don't know. So you get the GPU stuff up here. These are the sort of the heavyweight, right? The powerful processors, right? This is going to probably be like a centralized cache here. These are going to be the 4 core tiles. I'm making this up, but I've read enough of these. This here, I know this is outside of it, but this is really it's this box that they're labeling there. These are the little neural processing units, right? They're in here. And then we got the efficiency cores are going to actually be in here. They're not out here. This part right here is not labeled, but I believe this is the video encode decode would be like right down here, in here, right?
Yeah, so it's my understanding, like, so I'm like a Apple video encoding like nerd. This is something I was deep in back in the day because I was doing Hackintoshes and couldn't get the performance I was looking for, and then I discovered the Afterburner architecture and all the stuff Apple had done for like video encode and decode, which is overlaps with GPU stuff but isn't the same. It's my understanding that either in the neural engine area or somewhere else here there is the protege of the Afterburner chips that they used to make that is just H.264, H.265 encode decode. Like that's all it does.
Yes. And I'm outlining it here because I believe I know where it is roughly, but it's just not labeled on this diagram. So there'd be one like there'd be like a box around, I think, like roughly here. Right? Roughly in here. Okay.
Makes sense.
So here we can just pull up a die shot of a Zen 4 APU, right? So here are the cores, right? Here are the higher, the bigger cores, right? This is this was labeled again community. So community labeled as always by someone named Bus Alexi on Twitter. If you want to, I try to give credit to the people who labeled the things. But so you can look at this thing and it's like, okay, here's the cache again. Here we've got sort of the 4C cores are the smaller cores. There's you have that sort of big little. It's not exactly the same on Zen. Zen is not quite the same on their big little, but they do have this more compact version of the core. So these are the bigger ones. These are the little ones. There's the cache again. Here are the GPU cores in here somewhere. They're not labeled in a particular way, but they are going to be tiled in some way, presumably. Here's the media engine. That's the video part, right? That will do encode and decode. So it's pretty much exactly the same. If you go SoC to SoC, you see exactly the same things. You got your big cores, your little cores, you got your cache, you got your media engine, which has your video decode. So there's really no difference between Apple and anyone else on there. The only reason that it seems like, oh, well, the M series chips has it, but a Zen chip doesn't, is because we're thinking about a Zen chip that is not made for SoC. So this normally on the PC is on the GPU, right? So if you look there, it would have, if you looked at like the die shot of a GPU, it would have like usually labeled VCN is what they label them on the GPU, but on an AMD GPU, it's got video code, encode and decode on that because that's the more efficient place to put it, since that's where you're going to output the video from there, right? But if you look at the equivalent to an M series, which would be like a Zen 4 APU, where it's made to all be one die, where you've got the GPU smushed and the CPU together, you see that the exact same thing is true on a PC part as on an Apple part. They both have dedicated encode and decode exactly the same.
Okay. Let me reframe my take because this is good context for me to have, and I definitely was not clear with like the part I found interesting with this. Rather than like Apple being first here or Apple being the only one here, the thing that stood out to me was that APUs almost felt like a thing that were done after the architecture was defined, and like AMD's top of the line like chip, the like thing that they would push every year was their new CPU and also their new GPU once they acquired ATI. But those were like these two top of the line things they push, and then the APUs were more like not like the big hyped flagship thing. They were the best parts of those architectures boiled down to a specific chip with a specific need, usually laptops. What I found interesting with this was that this is the first time I saw a media engine on a flagship chip ever.
Yes, except again, the only reason for that is because they decided that their fab strategy was going to be that they weren't going to ship anything discrete, right? So I guess I would phrase this, they had no choice. Where else would it go, right? Normally, if you have a desktop where you're going to separate the CPU and the GPU because you're trying to have the GPU have its own dedicated high performance memory, that's separate from the CPU side, and you want to be able to swap them, and all these other things that PC enthusiasts want to be able to do, or who knows what. For Apple, it's just like, look, they have to have that to be competitive. You can't not have a video encoder and decoder because every PC has one, because either they've got it on the integrated die that they have on something like an APU, or they have it on the GPU. So Apple has to have it to be competitive in video. And so it had to go on the only chip that's really in the system, right? And this isn't just with APUs or that marketing term. If you were to look at Intel, like in the Skylake era, when they had their laptops, just Intel integrated graphics, that was a huge, for all that time, Intel integrated graphics, those were their flagship mobile parts. Those all had video codecs on them too. So that's just the nature of video encoding, that you can make some special purpose stuff to speed it up. And because everyone does it and they want to do it low power, and they, originally it was because they wanted to do higher resolutions and the CPUs couldn't do it fast enough. We can do it fast enough on the CPU if we want to now. But nowadays it's just like, we still don't want to do it on the CPU because it turns out it's just much lower power if we just bake in some of the stuff into one of these dedicated units. So they still do it.
That makes a lot more sense. I still am absolutely floored with like the things that you can do with Apple's media engine. I know others are starting to catch up, but the fact that I could have a like tiny MacBook Air using like 10 to 15 watts of power and real-time encode 2 4K streams on that box was absolutely unheard of at the time. And still to this day, like I could do my whole job from a $800 refurbished MacBook Air without any issue. I need to focus on the output, like the actual result of it, more than the pieces on how we got there, because those details both don't matter and I was meaningfully wrong about. So this is really useful in how I like explain these things, because Apple's care wasn't like where this goes. It wasn't some crazy innovation in how they architected things. It's just they had a specific goal and they achieved it because nobody else was trying to at the time. And now others, regardless of the technical implementation, are trying to achieve similar performance levels.
Well, and I would assume, although I'm not familiar with this specific thing that you're talking about, obviously, but I would also assume that Apple gets a lot of benefit by being a single unified integrated platform provider, right? So it's like, look, we know that we are shipping this exact M series chip and all Macs will have this for 2 years or something. So when you go to make an encoding pipeline, you can make maximal use of that thing. If by contrast, you look at the PC, it's like, well, okay, how are we gonna do that? Well, we've got to have drivers for it, because there's, is it a Zen 4 APUs one? Is it a discrete NVIDIA one that you plugged in? Is it an Intel integrated graphics media encoder, right? And so you got to do some lowest common denominator stuff there. You have to make sure the drivers are installed for all those things and that they all work correctly and they can all be leveraged, right? So I would imagine that Apple probably also gets somewhat of a win from the fact that they know, like, this is what's on the silicon. And so when we make the encoder, we take maximal advantage of that. And that's probably a win for them too, right? Because they don't have this sort of ecosystem to manage as a result. But
Absolutely.
I could be wrong. But I would assume that would be a big benefit to them.
Blackmagic even charges $200 for you to get GPU accelerated encoding in DaVinci on Windows. Like, you have to pay money for it.
There you go. So.
Yeah. Super helpful, super clarifying. Appreciate that a ton. Unless you have anything else, I think now is a good time for questions.
If I can answer them. Like I said, a lot of times my answer is, I don't know. I wish we had a hardware engineer here. That's the answer all the time, right?
Yeah. First question, when's the next episode of Computer Enhanced coming out? People are hyped for part 4.
Well, the first part of part 4 came out last week, and the next one will be probably tomorrow or the next this week, probably.
Super exciting. This is a fun one. Do you have any insight on the recent failures and stability issues with Intel's latest processors? Is it a production issue? Is something wrong with the architecture? I'll add one more. Is it part of the benchmarking race in order to look better than AMD by 1 percentage point?
I've heard a lot of different things about that. This is what was it, Raptor Lake having the instability
It
issues.
was 13 and 14 series. I don't know the names.
So I don't know. I really don't. What I have seen claimed in, sort of in Intel's kind of vague press release things, and also in, people who were finding these bugs and so are finding the instability issues and so on, was that, if you look at what happened with Intel and AMD over the past 10 years, let's say, you had this situation where Intel used to fab their chips themselves, and they were really, really good at it. They had the best process technology in the world, and that was really one of the reasons why they were a leading chip manufacturer. It wasn't just because of x86 64 being sort of like a monopoly for them. It was because their fabrication technology was better than anyone else in the world. And AMD, in fact, had trouble competing with them on that front because AMD had to use inferior process technology. AMD had their own fab. It got spun out, I want to say, as Global Foundries, which is now a separate fab. But it was an issue, right? AMD ended up switching to doing external fabrication. They spun off the foundry business. They switched to external fabrication, and they fab their stuff on TSMC. TSMC happened to just execute like times 1,000. Like they just were the most amazing chip fab. They every year got closer and closer to Intel, and then they overtook them. Yep. Intel had a process called 10 nanometer. That's what they called it anyway. And
we agree that those names mean literally nothing, that nanometer measurements are like measuring contest that doesn't actually measure anything anymore.
It has definitely been a problem because it's like it doesn't really tell you very much when you say that number, but they have names for them, right? And they'll talk about TSMC's N5 node or whatever now, right, or whatever. But anyway, so what happened at that point was TSMC actually ended up fabbing chips better than Intel because Intel's 10 nanometer fab technologies just did not pan out for them. And sadly for Intel, they ended up in a really bad state with their fabs. They just could not seem to get back on track for quite some time. So we saw this really weird situation where Intel had to keep squeezing more and more performance out of effectively the same process technology, only like one step down after that, whilst TSMC is constantly marching on and continues to improve their process technology. So AMD was able to basically build more and more competitive chips on that process, and they had always been good at design. So they were designing really good chips, and now they have better process technology. So their chips were just plain better. And Intel could not seem to produce, because of that sort of situation, could not seem to produce a really competitive chip without cranking up the amount of power that the chip was actually running on. Now, again, you'd have to ask an electrical engineer where these power trade-offs come from. But what you saw is AMD is like benchmark even with Intel or something, and they're consuming like half the power, right? And then they're benchmarking even with Intel to like a third of the power, right? Because Intel's power keeps going up, and AMD is like now like, yeah, we can do like 120 watts or sometimes 90 watts, 65 watt part that's competitive. It's nuts, right? They're going down while still ramping up their performance, and Intel is up here in these like, super, super high power draw wattages. So
yeah, I just an anecdote on that one. I recently put together a 14 series machine as like one of my stream rigs, 125 watt TDP. Do you want to guess what it runs at by default before I like fixed it?
What?
350.
Okay.
350 watts that thing was pulling. My power supply now whines.
Well, this is the situation, right? they were using a tremendous amount of power because they were trying to be performance competitive on older process technology and without a significantly better design. It might have even been a worse design. I don't know. I can't really evaluate those things because I simply don't have the hardware knowledge to know how they're doing. But the result of all those things, I think, just combined to Intel, you can't just push an arbitrary amount of power through these chips, I guess. This is what the electrical engineers say, right? You can't just crank it up arbitrarily. Stuff starts to go poorly. And my understanding was that was really what was happening. It was power management of parts of the chip, like trying to make sure that the voltages or whatever on these chips were not getting exceeded for certain parts of them. The ring bus, multiple people were talking about the ring bus, potentially this thing that does communication between parts of a chip, not being able to handle certain sort of power levels that were being punched through it, these sorts of things. So I don't know, and it's really not my area of expertise, but that was my best understanding from the things people were saying. It's like Intel was just fundamentally pushing too much power through these chips in order to try and remain competitive, and they just missed something, right? In that managing very carefully trying to manage the power so that you don't overheat or damage the chip or get a wrong result because of something. And they just missed it. And then they didn't know what it was, I guess, for a very long time, but then they eventually fixed it. Hopefully now, I don't know.
So that is pretty much exactly my understanding as well. The one additional detail that I remember vague parts of from a Gamers Nexus video, somebody else cited it, is that there was something about the manufacturing where like water was seeking in and it caused certain parts to be fine under their recommended loads. But since every single motherboard goes to those crazy wattages and Intel kind of encouraged them to do it, that the corrosion on like these like small pieces could fail much more aggressively if you put way too much wattage through it.
Yeah, I think that was, so at least according to Intel, they claimed that was like an early thing that got resolved and doesn't affect that many of the chips. But I think Intel has sort of confirmed that they didn't say exactly if it was exactly as Gamers Nexus said it was, but they more or less confirmed that there was a manufacturing defect. But apparently that was not the extent of it, meaning that was just some relatively small subset of the chips. And then even after that defect was fixed, the chip still wasn't properly limiting power to, maybe it's the ring bus. I don't know if anyone ever determined it, right? And so they were still failing even without a manufacturing defect.
Yeah. I remember something about microcode that was occasionally sending like just full like wattage down a pipe that it should be, that could cause one part to fail. And that's the update that they've been pushing. Like one of my machines, funny enough, you might have seen this when it happened on Twitter. Dell had a bunch of discounts around, I think it was Black Friday last year. Okay. And I got a fully spec'd, like decently high-end Dell desktop with, I think it was a 13700 non-K, 16 gigs of RAM, whatnot. 4090 for $900 for the whole machine. So I got a 4090 I got a full spec machine for less than just a 4090 retail.
How was it used? This is a new 49.
No, it was Dell had a bunch of discounts. They had a ton of discounts, and I had a credit with Dell from a recent purchase, so I managed to get a 4090 full desktop. And Dell's manufacturing of GPUs is actually really good. So I just took the 4090 out of it, put it in a different machine, and then put another GPU, and that's my like living room PC now. But since that one's Dell and I left it on the stock operating system because I always find it interesting what OEMs are doing nowadays. It had an aggressive like Dell recommendation update that I couldn't get to go away until I did it. It was the microcode patch because they want to deal with less RMAs.
Yep. Yeah. I mean, I don't know what else to say. Yeah, that was a really bad situation, and I don't know if it's fixed. I mean, they pushed those patches. I've
heard it's like fully fixed now. From what I know, the microcode op fixes has fully fixed it, but it doesn't undo the damage if you push the too high of wattage at some point beforehand. So it can't fix a broken chip, but it will prevent further breakage. And Intel extended the warranty to like 4 years now on those chips, if I recall. To like,
that's good.
They'll RMA them. Yeah. Okay. So that they're handling it well, all things considered. But what a wild journey to get here that was. And I'm just happy I get to nerd out about this because I've talked about this once or twice before on stream and nobody normally cares. But now I get to nerd out about these things because it's just something I happen to be really into. On that note, actually, have you chatted with the Linus Tech Tips folks at all?
No, I don't even know the Linus Tech Tips folks at all.
I'm really close with Luke. I love those guys a ton, and I know they would have a ton of fun picking your brain for stuff about this in the future. If you're down for that intro, I'd love to make it.
Sure. I mean, I'm happy to talk to anyone with, of course, the caveat that, not being a hardware engineer, there's only so much I can do, right? Yeah.
This higher level conversation about these things would be very helpful to a handful of people there. I personally know I would love to make that intro. It just comes to mind immediately as I talk about this. Because I normally nerd out about this stuff with Luke.
Okay.
Yes.
Gotcha.
They love this stuff, and they're like they are the ones that will help get this message to the hardest to reach demographic, which is PC gamers with bad assumptions.
Okay. Yeah, I'm always happy to try and help clarify stuff to anyone who wants to know. So absolutely, if they have things that they think I would be useful for, certainly.
More than happy to make that intro. I'm looking for additional questions. Someone keeps asking how you feel about the W3C standards, which are like the web standards. If you have an opinion, I'm down to hear it. But
they're poor.
Yeah,
I don't know what else to say. They generate a very large volume of stuff that manages to still not be able to do oftentimes even basic things you would want to do. So it's we
finally got the ability to move an element in the browser, like with a recent update.
Huzzah! Right? Yeah, not good. Not good. They make everyone's life a lot harder because if those specs were really good, the web would be a lot better. So that's really all there is to it.
Yeah. One that I actually think you might have interesting thoughts on. Somebody mentioned like OpenGL being largely dead. They were curious how you feel about WebGPU as the like pseudo replacement and the potential for WebGPU being people's both like introduction to graphics programming as well as a potential like landing path standard for things going forward.
Well, here's what I'll say. I think the era of graphics APIs is not going to be forever. If you take a look at the way that graphics APIs came about, it was because the hardware that we were programming for was extremely specialized. You basically had to announce every last little thing specifically through an API. Here are these textures. Here are these triangles. Here is the projection matrix I would like you to use for the triangles. And it is a projection matrix and all that sort of stuff. That was all because the hardware actually needed to know those specific things because that is exactly what it would do. It would like use this exact texture as a texture in this specific way on this triangle through this, blah, blah, blah. As we move forwards, you get to, things today where like, it's like, hey, they don't even use like the rasterizer in entire swaths of some rendering engines now. It is still used for things like depth prepasses and stuff like that, but like they write their own rasterizers and compute shaders because it's more efficient to do it that way than to push it down as a pipeline. And you got all this stuff with, bindless where it's just doing, memory accesses that the GPU hasn't even been told exactly what those things are, all this sort of stuff. And so I think what we've seen is really what programmers want is just to program these things the way we program CPUs, right? We just want to dump down, here's the code, just run it. Like, I don't want to be telling you like what my textures are. I don't want to be telling you what my, this stuff is. And unfortunately, there are still some limitations on that because of the way that you need to optimize like memory access patterns for some of these things. There's still some unavoidable aspects of like, yeah, okay, can we completely get rid of the part where you tell us this is a texture? Not necessarily, right? Or things like that. So there's some parts that still create a constraint. But on the whole, it's just getting less and less important what the API is and more important what the code is. So the shading language or the intermediate representation that you ship. So for example, WebGPU, I want to say, did not adopt SPIRV. It was recommended that they do, but they didn't. So they made their own text-based shading language. Am I getting that right?
I know that SPIRV is not part of it. I don't know how you would encode a shader in WebGPU.
I
I've
think they made their
largely
own
stayed
shading
away.
language. I think they made their own shading language. Is that wrong? Can someone tell me? Because I don't follow WebGPU that closely. But
Yep. I just found the WebGPU shading language W3C working draft document. So
Yeah.
yes, they made their own.
Yeah. So basically, what I'd say is, first, I try to be less negative than I used to be when I'm on other people's streams, especially.
Nope, mine's the one where you can go all out. Just do it.
But I try not to be on other people's streams. Even on my own streams, I try to be less negative now. But um, literally, no one in the world wanted another shading language. I mean, it's already a huge problem for developers that they have to deal with things like, oh, am I writing this in this shading language or that shading language? Well, I need to ship on both these platforms, so now I need to have like a thing that transpiles one to the other, or or a language that I create that outputs to both, or right. Nobody wants this. Nobody wants this, right? I mean, why do you program in something like JavaScript, right? It's because I just want to write the thing once and have it work everywhere, right? Well, the problem with something like WebGPU is it's like, okay, so what is the plan here? Is the plan that this will just be for web developers who will sort of write some stuff that they only write for the web? In which case, I guess it's not a huge issue that you made a new shading language that's your own shading language that then we have to worry about if there's any little differences, right? Hopefully, they made it fairly similar so that, but whatever. Well, if that's the case, then is WebGPU going to replace OpenGL? No, because it's only for shipping things specifically on the web. But if the idea is, well, we're going to use WebGPU more broadly, and we're thinking about this as something we're going to program in generally speaking, and we'll start to use it, we'll use that shading language for everything and that sort of stuff. It's like, well, okay, are developers going to switch to that? What is their incentive to switch to that? Most 3D development doesn't care at all about web. The web is mostly a 2D medium most of the time. How much do they really care about this? Not that much, I would think. So how compelling is it to switch to WebGPU if what I really care about is shaders? I doubt very much. So in terms of making a prediction, I can't say. But what I'd say is WebGPU doesn't really offer anything. It's like it's yet another shading language, which nobody wanted. Maybe we'll be forced to adopt it because it will just become a thing that becomes prevalent over time because it is a standard and it's being promulgated. But I don't think anyone is looking forward to this, right? Like, I don't think anyone wants this. What we would have liked is just a unified, like just pick one, take HLSL or something, and just that's what we're using for everywhere. That's what we would have preferred, but that's not what happened.
It's funny because in one sense, the web is good about that, where like JavaScript is the one language and standard, and now they're inventing new languages and standards for problems that exist outside. I did get some info from a few people in chat that apparently Apple was the big blocker of
That's
SPIRV,
right.
Which is...
That's right. Yes.
Apple continues to hold back the web. Ugh.
Apple absolutely ruined WebGPU because the initial recommendations was to take something standard like SPIRV so that you could just use your standard compilation path that you're using on something like Vulkan, and you could just ship those same shaders, right? And oh no, Apple had to come in, and this is not speculation. I was curious about it, so I literally read the meeting minutes, and you can watch the Apple representative say we're not doing that.
Yep, I've been there a lot of times with Apple Web Standard stuff, so not surprised, but ow. Yeah.
Good context. I really wish they hadn't done that, and that it really sucks.
Yeah. Last question that I'm particularly excited about. With all the changes going on with like everything from politics to leadership to manufacturing, how do you feel Intel stands now compared to TSMC? Are they catching up? Are they still falling behind? And do you see a future that you're excited about there at all?
My opinion of what Pat Gelsinger was doing was that he was kind of doing the right stuff, more or less. And I don't really know that much about running a Fortune 500 company, right? So I don't know, but he has an engineering background. He focused on trying to get the fabs back on track, which is a huge issue. And it just, the capital expenditures for stuff like that are astronomical. I mean, they're things that you and I can't really comprehend trying to manage, right? Like, I've never had to worry about deploying $20 billion efficiently
Yeah.
on a yearly basis to build physical stuff, right?
Physical stuff that you won't see any results from for at least 5 years, probably longer too, which is crazy. It's like investing in that level is unfathomable to me.
And it's I've heard it said that fabricating CPUs at scale like this is one of the hardest things that humans have ever done, and it is generally true. Like it is almost impossible to do these things at speed like they are doing them. And when you read about the process and the weird things about, like, hitting tin atoms with lasers at multiple times, the same droplet, like multiple times to scatter like light that you can't reflect off a mirror because it's too small, the wavelength. And so it has to go through this special, you're just like, you just read it and it just sounds completely fictitious. Like the whole process just sounds fictitious. And so, from an external observer who really doesn't have any inside knowledge, I thought that Pat Gelsinger seemed to be doing the best he could have done given the bad situation that he had. And I don't know whether he would have succeeded, but I don't know what else he would have done. Changing, like, sort of having him get pushed out and then switching to, like, I want to say the people they put in charge were like a CFO and a marketing person or something like that. Like, it was not, I don't remember who it was, but that sounds to me like, I mean, maybe Intel's just done. I don't know. Cause like, this is an engineering problem they're solving. Marketing, you can't market anything if you don't have a leading edge foundry. Like, there's nothing to market. And if they got rid of the foundry and just manufactured everything on TSMC going forward, what's Intel's value add? They don't design super more competitive microarchitectures than AMD. In fact, they seem kind of not as good currently at that. So what's the value add if they're not a foundry? I don't know what it is. So I would say, if anything, I'm much more nervous now than I was. How do you feel about it? I don't know.
My gut feeling is we don't know until the fab spin up and we actually see the results of the new investments there. Like, it either will go really well or it won't at all, and it's impossible to know. The only company that's like the two architecture companies that have their shit together are AMD and Apple. And Apple has no interest in selling their chips. God, imagine a Nintendo Switch powered by an Apple chip. It's a dream I've had for a long time. I'm still pissed Apple didn't buy Nintendo. That would have been better for basically everyone involved. But all of that aside, Intel doesn't have an advantage without the fabs going well. And I cannot see them being successful unless those investments turn out to be really, really good. The best bet they have is that tariffs are going to screw over all the people in manufacturing with TSMC, and they might get an edge out of that. But like, the GPU experiment has largely failed. It's heartbreaking. I was really hoping it would go better than it did, but it largely failed. And I don't think they have another edge unless they pull off fabs.
Well, yeah, I mean, I think that sounds like you're kind of in line with me with what I said then,
Yes.
right? Like, the fabs were very important. And I mean, I guess, how do you feel about the leadership change though? Because, like, it seems like the leadership change, if anything, is de-emphasizing the fab part, which is what was making me nervous.
I have so little understanding of the old and new leadership that I can't make a meaningful comment there. Yeah, okay. I have purely operated on like the products coming out and the plans that I have heard, not like the specific decisions or thought process of the like CEO there, which is unusual for me because I know a lot about Sue over at AMD, but I just don't know anything about what Pat's done.
Yeah, I mean, and we have pretty limited insight into that anyway, right? If you're not there,
Sue just got Times Person of the Year, I saw.
And she deserves that. I mean, if you look at Lisa Sue's track record at AMD, I mean, it's kind of spectacular. Like, I'm
at 250% up on my AMD investment right now. I'm very happy with that one. I haven't bought an AMD chip for 11 years, but every time I buy an Intel chip, I'd put the same amount of money into AMD stock, and it has worked out very well for me.
As a programmer, I absolutely love Zen 4, and I have a Zen 5 now, but I haven't really taken a spin on it at all. It's on a kind of separate machine. I change dev machines pretty slowly, so I haven't, but they are just fantastic to work with. I love them. And so and you just look at the track record of the decision making there. It's been really, really spectacular. Deciding to go all in on chiplets and Infinity Fabric, deciding to use an external fab, like all these things. And I want to say that most of those decisions, if not all of them, were decisions that got made under Lisa Su. And so, yeah, I guess you could argue that maybe the AI GPU side hasn't gone as well for them. But I mean, they came into this not having the kind of resources that someone like NVIDIA or Intel had. They were starting from a very underdog position. And so even executing on one side of that, like even just executing as well as they have on CPU is remarkable, and very few people probably could have done it. So I feel like I didn't know she had gotten Person of the Year, but she deserves it. She's easily one of the best CEOs in the hardware business, full stop. And it's that probably just means one of the best CEOs, period, because the hardware business is the hardest business. You can't really, I mean, there's like SpaceX or something would be the other things you might think of that are that way, right? But it's like, this is the hardest business.
Even to go further, they're like winning one vertical of CPUs, like the way that they won like APUs with game consoles, or the way that they won low power with things like the Steam Deck and handhelds. Like any one of those wins would be monumental. The fact that they've fully pulled over CPU are like investment to their side. Like server farms aren't picking Intel right now. That's unbelievable.
And that is the most important market segment for those vendors. Like they want data center the most because it's the highest margin, right? And so the fact that they are able, like this year, I would imagine that build outs of data centers are largely AMD. I mean, they have the better chips, and their chips, Intel's chips, are not anticipated to be competitive next year on data centers. So, you know, it's really pretty remarkable. And yeah, I don't know how they did it, but whatever she's doing, she should keep doing it.
Yeah, I lied. I actually do have two more questions. Hopefully, one should be quick. One I would like to be quick, but I know it won't, and that's fine. Okay. And if you have to run, that's totally fine too. No pressure at all. But
oh no, it's totally fine.
Awesome. So the first one, I saw this a while back. I can't find the person who shared it that I thought was really good. What are the current bottlenecks for processors, and do you see that changing going forward? Like, what are the things slowing down our chips today?
Programmers. Full stop. It's the programmers are the bottlenecks, and you can really see this in the chip designs that we have. So the problem with the current model of programming, especially on the CPU side, is that we sit down and we write down a linear series of events, and most programmers spend almost all their time like doing that. They're like, I'm going to add these two things together. I'm going to look at this thing. I'm going to look this up in a hash table. I'm going to do this if statement. This, then this, then this, then this, then this, then this. Giant serial dependency chains of things that have to happen. And we long ago hit the limit for how fast we could execute serial dependency chains just straightforwardly. So all of those things that I showed on that CPU architecture diagram, why am I decoding so many instructions in parallel? Why am I doing all these things from this instruction stream, executing them specularly? Why does the branch have to guess, right? All of that stuff is because they're trying to mine parallelism out of some thing that you said had to happen in order. And so they're just looking for things that can go out of order and looking for things that can start ahead of time. And they're trying to do all this stuff, right? If instead we had a programming model that was more like what GPUs use, right? A programming model where we're thinking about doing millions of things always, right? Like how are we going to shade millions of pixels at a time and do millions of triangle transfers at a time, right? Millions. The architectures can be much more efficient. You ask yourself, why is a GPU different than a CPU? What like, is NVIDIA just better at making stuff? Like they're just that much smarter than Intel and AMD when they make CPUs. So when they make a 4090, it's just that much better. It's like, no, it's because they are able to just concentrate on parallel execution, right? Because the thing they're being fed is inherently parallel. You take AMD itself. Why does it's the same company, right? Like AMD. Why can their GPUs do so much more rendering than the CPU could have done by itself? Again, it's phrased as a perfectly parallel problem. They can architect hardware to just do it perfectly parallel, right? Mm-hmm. And I'm glossing over a bunch of stuff there, but there's also like memory stuff, and there's other reasons. So I don't want to make it sound too simple, but at the core, that's sort of what it looks like.
And for tasks that are complex enough, we just have to go that way. Like things like training AI models. Like if you don't do it in parallel, you're not doing it at all.
will never finish, right? It'll never finish.
Yes.
And so when we look at something like a CPU and we say, what is the bottleneck right now in terms of why it can't run faster for whatever the thing is we're looking at, it's programming. We could trivially have made it run much faster if we were programming it fundamentally differently, right? And so usually we are the weakest link. And what we're seeing when we see these CPUs that post what we consider to be impressive gains, oh, there was a 15% or even a 20% generational uplift in performance between this CPU and that CPU or whatever. Really what we're seeing is just them compensating most of the time by mining more and more parallel work, or fixing more bad access patterns by increasing the amount of cache, or fixing the fact that we were lazy about how we stored things, right? Like they're just basically trying to paper over our bad job. It's not always true. Like sometimes it's like, no, I really wrote a great program that's really well optimized and it just needs more cache and they gave it to me and it's faster now. So it's not always the case, but a lot of times we're the weakest link. We're not feeding them parallel enough workloads. And so the biggest thing that could improve is our programming model. If we take that out, which is a pithy answer, then it's like, what's the bottleneck? I mean, you'd really have to ask a hardware engineer. A lot of times on, it's just how much do you want to spend for this CPU? They can always add more of those ALUs, more schedulers, more decode units. That's what you saw when the M series came out. They decided to do a really beefy everything, and it performs better. So the bottlenecks are really just adding more of those things, adding more decoders, adding more execution units, adding bigger execution windows, all that sort of stuff. And that's also why we care about things like improving the process technology, like the shrinking dies and that sort of. The more you can fit on there, the more it can do in parallel.
So we need to put JavaScript V8 engine onto processors going forward, is what I'm hearing.
No,
just bake it in.
We need to stop programming in JavaScript. Might be a start, but it's not going to happen. So,
hey, what if we just compile that to assembly? Then everyone wins.
Well, what you could do, again, like I said before, is if the programming model of JavaScript are different. So fundamentally, what happened was the programmer writes down this thing that's going to like how batches. Everything is batches. I'm going to do. Thinking in terms of hundreds or thousands of things at once always, instead of one at a time, right? If you had a programming model that was more batch-oriented like that, then, yeah, it wouldn't matter that it was in JavaScript, because the V8 engine would know, oh, this is all batched. I can make all of these things be done wide and on SIMD units and across many threads at once and all this stuff, right? And all of a sudden, things become a lot easier, right? And so you could imagine a future JavaScript written with shader mentality, and that could be something, right?
Yeah. I will say JS has some of the better like baked in concurrency. If you eat the fact that it is like everything is done like synchronously on the main thread, the fact that the async model allows you to put tasks on the queue that are running in the background as you keep chewing through the synchronous work is really powerful and allows you to do a lot more in a single thread than other languages by default allow without diving into like parallelism. The fact that like I can have an application where thousands of users are going to it and all of those requests are IO bound on a database request, and I can process all of those thousands of requests at the same time, even if the actual process of generating the response is done fully synchronously on the main thread. Pulling out all of that work is really beneficial, and there could absolutely be a model in the future where more and more of that work is broken out that way. The workers model that we have in JavaScript is fucking garbage. I hate it so much. I've worked so hard to make cool things with it. Like I did a video recently. I made the fastest server render JavaScript framework. It's like 10 times faster than anything else, and it's entirely based around hacks of the parallelism that we have using workers, and it is not fun.
Well, yeah, I mean, like I said, it can happen, right? Like you could imagine moving more and more in that direction, because there's nothing inherently stopping people from taking JavaScript and saying, what are the ways we could make this so that it can execute wide on like SIMD? What are the ways, right? And because it already does, it'll, the JITs will already take advantage of those things when they're available to the extent it can. It's just the programming model doesn't encourage the programmer to do things that will that will have that end result, right?
There's also no way to share memory across threads other than crazy string manip bullshit right now.
Okay,
And
yeah,
that's being
that's bad,
fixed.
right? Yeah.
There's a proposal for shared structs that is really cool. I also did a video on that. I'm super, super excited because we could finally like have an object and have an unsafe like block
Yeah.
that says we're accessing things here, build your own mutexes and whatnot. That will enable a lot of these fun things. But we have a ways to go till we're there, and we're still like generations away from what goes on in GPUs. I saw somebody said earlier, I want to find the exact quote, so it was really good. This is from Lucian Galaxy in chat. I got blown away when I realized I could process 4 million data points in 100 milliseconds without even breaking a 1% utilization on my GPU. And then I found out that 90% of the 100 milliseconds was my bad communication with the GPU.
Yes. Yeah. I mean, computers are way faster than most people experience, right? Because there's just a tremendous amount of waste in there. And I mean, I don't know what to say.
So the fact
That's why I try to get people to know more about stuff like microarchitecture, because once you start to realize just how fast these things are and how much power they have, you realize just how underutilized it seems to be all the time. Yeah.
I'm going to be in so much pain going back after stream to work on my game that I'm building in JavaScript in the browser. It's going to hurt so much after this.
Well, I mean, like I said, JavaScript V8, I think will do stuff with reasonable code gen if you drive it properly. So that maybe that's an excuse to go look at some of that stuff. I don't know what the easiest way is to see what the JavaScript JIT will produce for your code. Is there a nice tool that will show you that? I don't think Godbolt has that, but
nope. And on top of that, it doesn't immediately JIT the code. It has to decide that code is being hit enough that it's worth JITting in the first place.
That's how JITs will often. And they also usually have lazy optimization too. They might do like, oh, is this a important path? I'll optimize it more heavily or something like that. Okay. But yeah.
Okay. Actual last question. This one I thought of just because of what's going on right now. Quantum compute. How you feeling about the recent stuff?
Literally, I am completely ignorant of quantum. I have no answer. It's one of those things where I just assume that there are smart people working on this and they will let me know when I need to start programming it, right?
Did you see Google's recent announcements here, though?
I don't know anything about them. What did they say?
They have a chip working. I think it's called like Deep Freeze or something. It's going really well. The big thing they've been exploring is like error correction of like bad qubits, and they've learned that larger dies are actually easier to correct and identify bad nodes in, and they've been expanding their process to have way more nodes now because of that. And the results that like they have a much higher qubit count and it's significantly less error prone, and they were able to crack an RSA key like really quick with it.
How big was the key?
I don't remember.
Oh, okay. Yeah, I mean, unless it just falls apart at some point, it's going to be a weird day, because I mean, so many things are built on the assumption that you're not going to crack like elliptic curves, that, cryptocurrency is built on this, communications built on this. So assuming that they do, and everyone has to switch to quantum secure stuff, I don't know what's going to happen. Like it's not my area of expertise, but it's a bit scary, certainly, because I don't know who's going to do all that work or how. I mean, I read occasionally DJ Bernstein stuff where he talks about, here's like quantum secure alternatives to some of the cryptography that we do, but it all sounds very expensive compared to what we're doing currently. So I don't know.
Does anybody in chat have the specific challenge that Google completed? I heard about it, but I'm like, all the articles I'm clicking are paywalled and I'm getting very annoyed.
Okay.
I hate how this info is being abstracted. As the web dev in the room, I'll take the L here. Where is it? I'm so curious. I know there was some specific challenge that like supposed to take many years to complete, like over 100 that they completed in like an hour. I can't try to remember the name of that challenge. God, what is it? The Ice Cube challenge, apparently. Oh, somebody found it. Of course, it's playing a... Oh, I was muted there. It's playing an article video in the middle of the article. God damn it. Qubits packed onto a chip. Error. Solving a computing problem in 5 minutes. Okay, they solved a computing problem in 5 minutes that would take a classical computer the time of the universe. Cool. That's not the answer I'm looking for. Okay, here's the page. It's quantumai.google is the URL with it.
Okay.
Yeah, of course they're using their .google TLD for once. State of the art. Where's the? Show us the actual challenge. Google. This is my problem with all the quantum stuff is like they don't give me any actual info. It's just like they say all these things over and over.
Yeah. I mean, like I said, since I don't really know anything about it, I just know like, okay, well, here's what theoretically a quantum computer would enable us to do. And I'm just like, well, I don't really want that. Because like so far, I'm just like, I don't know what we would do with this other than break all the current cryptography stuff. But I guess maybe there's other practical uses we would care about where you can, where we care about solving n-squared things.
Yeah, I'm not excited for encryption to break. This
it
already
just seems
seems
like,
capable.
Yeah, I don't know.
It's like a state actor can break encryption is what I'm getting out of this. Not like this is way better for compute and going to change how we like write software. I found the number I was looking for. The random circuit sampling benchmark would take the fastest supercomputers up to 10 septillion years, and they did it in 5 minutes with their new quantum chip.
I mean, well, it's cool anyway, right? I mean, it's cool that they're figuring out how to actually compute with quantum because, I mean, for a long time, no one really knew if it would actually work in practice to do things faster. But, I mean, it's pretty magical stuff. But again, I have no reaction other than it's pretty cool. I'm worried about what will happen to cryptography because basically we will have to switch to post-quantum stuff, which will all be much slower. I don't know what like Bitcoin people have planned. I
didn't even think about the impact on crypto. God.
Like, I don't know how many of those have a plan for how they will be quantum secure. I imagine some will have more of a problem than others. But since I haven't really ever looked at that, I don't know. Maybe they'll be just fine. Or maybe it'll be like, oh crap, Bitcoin's done. Yeah. I don't know.
Ethereum has a plan for it. I did know that. Somebody called it out in chat. Nobody knows what Bitcoin's doing. Nobody ever knows what Bitcoin is doing.
Fair enough. Although it's the most popular. I love that. Like no one knows what Bitcoin's going to do, but it's the most popular.
God. Yeah. Right. I think that's all I have for questions. Happy that I could finally find something you don't actually know that much about. Not that I am any further along.
I know literally zero about. So it's
Yeah. So that's all I got. What do you want to shout out? What are the best places people can go to hear more from you and support you?
Well, actually, I mean, you can just go to computerenhance.com. And that is where I put all of my learning materials. We have like free stuff up there. And then I also have like a paid thing. You can go if you like this sort of stuff. And yeah, it's been really popular and that's been awesome. And so, yeah. It is literally all the stuff that we talked about on this stream, right? It's like, it's just talking about how you start with code and you look at how a microarchitecture runs it and you learn kind of how that works and then try to generalize that up and think about your daily coding choices, how you can sort of go like, oh, you know what? I can just be way more efficient now that I kind of know what's going on at the low level. So check it out. If you want, throw your email address in there. We'd love to have you.
38K subs on a Substack is absolutely insane. Congrats on that. That's huge. Also, the domain is so good. Computer Enhance.
This is me photoshopped into that Blade Runner scene where he's like looking into it and it keeps zooming in, right? So yeah.
That's so cool. I love it so much. Yeah, this is the easiest recommendation in the world for me. I know a lot of you watching, if you made it this far into the video, if this ends up on my channel, which I almost certainly will, you probably spend a lot of time in the JavaScript world. This is a way to break out a bit. I know how easy it is to get like rabbit holed in where you're so deep in JS you can't see anything else. It's happened to me before. These are the things I consume that I watch. Like I go to AnandTech, I go to Computer Enhance, I go to all of these types of sources because I like to know these things and I like having the diverse set of things going on in the computer world, because you could live your life at any one of these abstraction levels, but you should understand the other ones too, because in the end, some work you're doing is working alongside these other things. Stuff that Casey does is the building the systems that my shitty JavaScript code runs on. Things that we do in JavaScript land run on these lower levels, and these are going to matter more and more over time. Like, it's important to have this diversity in the places you go to get information about how computers work, because at every level it's different, and Casey is one of the best sources for the lower level stuff that I don't talk about enough here.
Thank you very much for that endorsement. I really appreciate it, actually. And one of the first things that's in like some of the materials I have up there is I actually look at Python, and I show like, okay, let's just look at all the instructions that have to happen if a Python program wants to add like that A plus B. And a lot of people really enjoy that sort of thing, because like, I like, look, we can actually tie this directly down to like a microdictionary. And it's shocking to people, because if you look at how much work some of these higher level languages actually require to get simple things done, it's actually rather remarkable. And so having that kind of understanding helps a lot, at least I think, in making sort of high level decisions about which language to use or about how you're going to do things. So yeah, I hope
absolutely agree. Yeah, I'm going to pay a lot more attention to computer enhanced. You said episode 4 is coming soon, right?
Well, part 4 has started already. So first video was last week. This part 4 is just about basically compute. So the previous part 3, I just looked at memory, and I basically was showing, because it was, you can go back. It's got a table of contents, so you're meant to kind of start at the beginning and work through it if you want it to do it like a course where you like learn everything. And so in part 3, it was sort of an introduction to that, like that Zen 4 diagram we're looking at, introduction of actually thinking through that and understanding how it works with respect to memory movement. So we're moving memory into and out of the core, reading, writing, and like also things that happen in the operating system with like page mapping, address translation, like all this stuff, like learning how that whole system works was part 3. Part 4 now is about computation. So how do you drive those units at the bottom, those execution units? What kinds of stuff can they do? What determines whether or not we actually get good usage out of them? And so that's what all part 4 is. And just using concrete examples. And we do a lot of like micro benchmarking, like where we run things and I show you how you can actually measure, like, oh, you see, we put this little thing in there and all of a sudden it's half as fast. Why is that? Well, here is why. This is what's happening inside the CPU. And so I try to teach like really hands-on, so it's always very concrete.
I love that. There's not enough of this in the lower level space. Everything is so abstract and like not even giving you the information, and when it does, it's not showing how it's relevant. That's been a struggle I've had forever. I feel like the things I read about on a non-tech and the things that I write in my JavaScript world, like the bridge it's too wide a chasm, and you have filled the in-between, and I greatly appreciate you for doing it.
I you know what? I'm happy that it gets this much attention. It's been really great. And thanks for having me on the stream, which I don't think I actually said so far. It's been really fun. I was looking forward to it, and it was every bit as much fun as I thought it was going to be. So thank you so much for being such a gracious host and having me on. I really
appreciate it a ton. Thank you so much, and I'm happy Ping survived the 4 hours straight. Normally, there's some form of desync at some point, but this went surprisingly well, all things considered. So again,
do you make this? You made Ping?
Yes.
That's amazing. That's awesome. Like I've used it before. Like Prime sent me when I went on his channel, he sends me a link to it. So I didn't even know you made that. That's awesome.
Yeah,
thank you very much.
I made this before I was even like really a content creator. I worked at Twitch for 5 years. I quit, joined a startup during COVID, went insane, quit, started looking for other jobs, and had 2 other founders bully me into making Ping a real business. I was working on it on the side for like helping friends do live collabs, because it was just so hard to bring guests into OBS.
Yes.
Like it's just not fun. So we built Ping to make that way easier. For those who don't know, ping.gg, it's like Zoom, but for content creators to do live collabs. All the other tools were too focused on like doing a podcast or using their desktop app that sucks. Nobody wanted to just make something that plugs into OBS that's as easy as a video call and meet. That's why we built it. Did really well. And like initially, I'm still blown away with how quickly it blew up, but it peaked relatively quick. So the number of people who were interested in high quality live collabs is relatively low. We have since pivoted to focusing primarily on dev tools. We still maintain Ping. It's still used by like most of the top 100 streamers for their live collabs. Like Austin's show has a game show every couple months that gets like 200,000 live viewers and millions afterwards. They've been using Ping for that for like 2 years now. Any like high budget collaboration production live, there's a decent chance nowadays that it's using Ping.
That's awesome. And I would assume, yeah, that's one of the business challenges there is just it's like, look, this is for streamers of which there aren't enough, right? I mean,
Mhm.
it's a small market, unfortunately, right? So yeah, I imagine it's hard to figure out how to make
Yep.
it self-sustaining in that sense, but it seems like a really good system anyway.
Yeah, it works incredibly well. We built everything we could want and more. I started streaming more and doing collabs like this more to better understand what creators needed. Accidentally got really popular on YouTube after I started the business in the developer
Okay,
space. And that's why we're all here today. That was an accident based on my attempts to better understand the market that Ping was built for.
that's awesome.
Yeah. Like I'm a web dev CEO first and foremost. This YouTube thing is still, I still pretend it's a part-time job. It's hard to pretend nowadays.
Accidental YouTuber. You fell
Yes.
into it. Well, that's
Mhm.
great too.
Yeah, but it's awesome to hear that you've been using the product and it works well. I'm pumped that it held up as well as it did here. And again, thank you for everything. This has been super, super cool.
Oh, it's my pleasure. Anytime. If you want to have
Yep.
another chat sometime, just let me know.
Yeah. And if you don't hear back from me by like Friday with the intro that I offered earlier with LTT, DM me. I'll make that one happen. They would have some really good opportunities to collab with you, I think.
Sure. And maybe we will use ping.gg for that as well.
Not unlikely. I've been trying, they were using Ping for a bit. They moved to vMix because they wanted to move off OBS, but hopefully I get
Oh,
back on Ping soon.
all right.
Good stuff. Thanks again for everything. If anybody wants to find Casey here, computerenhance.com, best place to do it. Check out his YouTube videos as well. Your Twitch account, do you stream particularly often?
Almost never.
Okay, I won't shout out the street or the Twitch, but it's Molly_Rocket, right?
Yeah, you can also find me on Twitter. I'm just C Muratori on Twitter as well.
Awesome. Yeah, I will grab, if a mod could grab that link and share it and pin it, I would appreciate that. Yeah, thanks again. Really appreciate it.
Thank
Cool.
you. Have a good one.
You as well. Peace. Give me one sec, guys, to wrap things up on my end. I'll be right back. Hi again. I am going to go to the bathroom quick, so I'll be a few more seconds. Just wanted to say, like, that was absolutely awesome. Again, huge shout out to Casey. That was great. We'll be back, probably hang out for another 2-ish hours. Team, I don't know if Ben's here. I think Gabriel's here. I know FaZe is here. If y'all can go through and get me a list of top priority things to cover today, that'd be really cool. Be right back. Gonna start again in a sec. I have to start the camera recording, which I forgot to. Not that it really would have mattered for any of that. Offset's gonna be 3 hours and 49 minutes. Cool. I don't know if my code is smart enough to handle an offset being after another marker. Only one way to figure that out. Oh, is OpenAI down? I gotta get a good screenshot of this. Thank you, chat, for the free tweet. You know, I always appreciate those. $200 a month. Don't people being mad that the guest isn't here because they read the title and expect the guest to be here. Thank you guys all for the kind words about the interview. That was awesome. It's all him, not me. I did an okay job as the host, but he did such a great job as a guest. That was awesome. It's almost like he's done this a bunch of times and had a plan going in. The fact that he had numbered out folders to go through each of my misconceptions, that was nuts. Super fun. That was a great conversation. ECMA approved of a source map standard. That's unexpected and really, really good to hear. Let me see. Seeing what we have here. Anything that's particularly critical. Oh, I did want to do the stuff with Brand Shield and itch.io. I want to film a better intro for this. My cast just knocked over the guard. Give me 1 sec. Oh, never mind. Mark's doing it for me. Thank you, Mark. Cool. Let's film that separate intro for this quick. Oh shit, new anti-res. There's so many things I want to read that aren't good videos. I spent way too much time yesterday reading through the first court proceeding with the preliminary injunctions for the WP Engine WordPress case. But that's not a video. Apparently, Anti-Res is going back to Redis. This is very exciting for me to read later, but I can't do a video on this. I don't know how to brand that. I don't think people care. It's exciting to me, but not in a way that I can reshape it for a video. I'm still on Pocket as my solution for saving things. I have 2 extensions that I'm considering remaking for my specific needs. Those are Pocket and Waffleizer. They both seem easy enough to remake, which might be me being arrogant, but I would love to do my own version, so I don't trust either. Someday. These are all on the list of things I want to fix eventually, but just aren't priority. If it's saying to you, just do it. If only my life was that simple. What link? Bean. Voltage helps increase frequency. Ooh, it's actually interesting. vaguely understand, not enough to re-explain to others. Should have asked this question, but I feel like we already got too much out of him. That was WP. Not only did I hear WP Engine is winning, I was like the first person to break that news because I was like so closely monitoring WP Engine. Like I had them on notifications for push for their Twitter and shit. And I read through the whole fucking like 48 page doc, I think. We didn't do WASM, don't worry. For Kubernetes spoof that builds everything into one service, so you don't have to keep dealing with the 5 million microservices. Oh, yeah, I'm sorry. So the equivalent of like micro front ends for your backend that isn't just microservices still doesn't really exist, like a proper architecture for that. I've seen a couple people playing with that. One of the companies I'm in talks to possibly invest in is doing that. Don't want to share too many details because I don't know them yet. We haven't done the call, but yeah, interesting problems for sure. Anyways, I need to film this intro quick. I think I have an idea for how I want to do it. Cool. I don't think we'll have ads on this. I don't think it's going to do particularly well, so we'll just go straight in. A few months ago, I did a video, or was it a few months ago? Yeah. You might have seen a video I did about x86 and how it's trying to be saved. If you're an architecture nerd, okay, better angle. I know you guys know me for JavaScript, but I am a pretty big hardware nerd too. Everything from CPUs to GPUs to hanging out with Luke from LTT. I care a lot about hardware, but that doesn't mean I know what I'm talking about, as I quickly learned when I made a video about the x86 working group that got formed a few months back. Thankfully, there's a lot of awesome people who watch my videos that are there to correct me, including Casey Muratori, absolute legend in the game dev, hardware, encoding, all of these spaces. He knows what he's talking about. And he very kindly hit me up to, as politely as possible, tell me that I was wrong about almost everything I said in the video. He wouldn't put it that way. I will, though. I did not do a good job explaining these things because I was explaining them from a software dev's perspective. And in that sense, I did okay. But once I tried to make assumptions about how the hardware actually works, I fell apart fast. Thankfully, Casey's a bro and offered to come on stream and clarify all the misconceptions I had and made some really interesting points. Specifically, he pointed out that most of the info I was wrong about isn't info that's accessible or available. It's not like AMD just posts about how these things work. None of the hardware companies actually share this data, so we have to figure it out ourselves and reverse engineer it. So if you want to actually understand how processors work, and also if you're a web dev, how these things affect our work day to day, I think this is an awesome... Oh God, I just saw the runtime. I'm sorry. I'll do my best to make this less painful and not put any sponsors in. Trust me, this whole thing is worth it. This was an incredible conversation, and I'm, again, really thankful for Casey. If you like what you hear, check out if you like what you hear from Casey, go check him out on computerenhance.com. Really cool. It's a really cool newsletter full of awesome stuff all about these things. He plugs it in the end too. Without further ado, let's hear from the expert. Cool. Actual intro now. Nice. Show the Computer Enhance website. When I mention it, might make cuts over my stammering easier too. Cool. New APIs. Oh boy. This is very interesting. This is very interesting. So you're saying this is good for accessibility? This has the potential to be good for accessibility, but when initially implemented, it's going to be terrible because none of the tools are going to know how to trace these paths to figure out which button affects which dialogue. So it has the potential to long-term be good for accessibility, but in the short term, it's almost certainly going to be bad. So, yeah. Oh boy, a package I was excited for got here. That makes me more likely to wrap up slightly earlier. Cool. What do we have for top priority items, team? I don't think I'm going to cover Willow. I don't have enough to say there. I love Leah too much to dunk on her again. I've done that in the past accidentally because I went into a video planning to agree with her and ended up disagreeing by the end of it. It's been a relatively quiet week for dev news, even though everything else is on fire. This is our planning internal Discord for the content team. This isn't a public one. It wasn't a Christmas present. It was a Black Friday. It's an iPad. I finally got an M4 iPad. I've been using a 6-year-old iPad now for 5 years. So it's a 28. Yeah, I've been using a 6-year-old iPad for 5 years now. So finally going to get a new one for the first time. It was like $800. I'm excited to try it. What is a good use for an iPad? That's a great question. Hopefully I'll have an answer in 2 weeks. Otherwise I spent $800 on bullshit. Yeah, this is really cool. I'm going to put this in the list. Not for today. Good call out, though. Thank you for bugging me to check that link. Video demoing the API. Let me grab this to have for later. Oh, it's the next one, guys. Dope. I will save that for my own research. Honestly, I'm going to watch later it. How about sub to syntax? Save, watch later. Cool. What did I mean when I said I was getting AI pulled on Twitter? I mean that I'm using AI for more and more things and finding it more and more useful. Like, I'd say I'm at the point where at least half of the work I do on a computer, I involve AI at some step throughout it. Like when I'm coding, I use it a bunch. When I'm writing, I use it a decent bit. When I'm doing graphics for thumbnails, I use it at least for like sketching out ideas and coming up with stuff. Like I used it yesterday when I was doing the thumbnail for my most recent, the Astro video, because the Astro asset I had was like letterboxed weird and it got cut off here. So I used Midjourney's editor to extend the image so that I had enough room to put myself into it. The money burning, this was also for something I posted yesterday. I finally updated my blog. And funny enough, what happened here is I wrote like a list of bullet points. I gave it to O1 asking if I missed anything. It gave some suggestions. I used like a third of them. I wrote out a thread on Twitter that I link at the bottom. It wasn't a thread. It was like a long post on Twitter. Wrote this out. Then I gave this back to ChatGPT and said, hey, make this an actual article, respond in Markdown so I can dump it in my blog. And that's what I did. So yeah, I've been using AI for these types of things more. This is still down? Holy shit, it's still down. Ooh, Gabriel. Good point. Good point. I hate Twitch. Oh, did Zen happen? Did they ship their beta? Oh? 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 Okay. Okay. I don't know if this is a video or not, but someone mentioned the Zen rebrand in my chat. I've been eyeing Zen for a minute. It's likely going to be my next browser, even though I don't love the Firefox base. But what? This just looks like a less pretentious version of the old Arc homepage. Whew. I am excited. I have been putting work into getting Zen how I like it, and I've made progress, but it's not quite there. At least it wasn't. I've been told specifically by people on the team, wait until this specific release. I'm going to do it and give my honest thoughts. I don't know if this is a video. I don't know if it's a main channel or second channel. I don't know anything yet. All I know is I'm excited. So let's do it. Will I find the new icon? I did. Nice. Open. This is honestly a little hilarious. This really does feel like Arc 2.0, but for real. It's hard to see the dark here. Just a little bit of feedback to see the outline there with the dark background. Oh, that's a weird... It looks like these are selected when the purple's the select. That really threw me for a sec. Tiny feedback, things they can fix very quickly. Okay, it's that everything I needed is here. It insta open closes the sidebar, which isn't the case with Arc by default. It's animated, which causes a lot of weird jank. You might not be as visible in a 30 FPS video, but the immediate... Command T. Weird. This might be because I have an extension for it. Testing. Okay, this is cool. Or corgis, !GI using a bang on DuckDuckGo. My DNS appears to be screwy. DuckDuckGo's been really bad at resolving bangs for me recently to the point where I almost made an extension to do it myself. I should go uninstall all of my extensions I have for Zen mods because they're different from extensions. Gonna disable all these. I'm gonna close and restart just in case some of those mattered. This is the article I had open, how to make Zen feel like Arc. Testing. Oh, it just does that by default now. Corgis. Okay. I think all of my needs are met. I'll be real. I don't know why I can't resize this. was definitely able to in the past. I remember there was something about a like I'm trying to remember. There was something about how in compact mode you can or can't resize this. This is probably just a bug, but look and feel. If I turn off compact mode, it might let me. I remember that being a thing before. Disable that will let me resize. Nope, just a bug right now. Annoying. Right click and you can just remove them. Okay, that made it smaller. Am I not already in compact mode? Okay, I don't want this. Remove from toolbar. Remove from toolbar. Move from toolbar. Apparently this is what was causing the size to be as big as it was. That makes sense. Can I not remove that? Tabs on the right? You guys have no idea how bad I've wanted this and how long I've wanted this for, because this puts it under me. This will auto cut. Oh my God, that I might move just for that. I might actually move just for that. I've been legitimately considering changing how my stream is laid out to move my camera to the right or to the left so that it covers the other side when I have my camera open. Oh my God, they did it. I think I'm moving to a Firefox-based browser. Holy shit. I never thought the day would come. Let's go back to the homepage and hear more about the wonderful things that they are working on. The top being like cut off like that is weird still. Is that because I'm not in compact mode? How do I move that away? Command Shift B. Nope, that just hides and shows it. Is this a consequence of moving the tab bar? Maybe in compact mode. Nope. Remove bookmarks bar. Okay, so if I options of C, no. Double click it. Any other genius suggestions? That's the address bar. Where did I scroll past it? This is just for suggestions. It's not what that is. Look and feel. I'm right clicking. It isn't removable. I'm going to close and reopen, see if it's just like a bug. No, okay. I don't know how to get rid of it. I am right clicking on the toolbar I want to remove. It doesn't do anything. I'm trying this, guys. I know how right click works. Now I have it set to never show, and it still has this section carved out up top. There is no bar here now. You can't get rid of the top bar with tabs on the right. That appears to be the case. Oh, so where'd the window UI go? Because my guess would have been they did that because the window UI needs to go somewhere. But there's no window UI here. Yeah, I don't think it's going to be a video yet. I want them to fix all these things. We'll save these assets so we have them for when I do a video on it. It's so close. But like even compact mode when it's on the right has the bar. It just has to be a bug on Mac. Yeah, just moving that to left kills that top bar immediately. Oh, look at that. Look what's back. If I turn off compact mode, I have my window UI again. I'm hitting edge cases. I know that's what I'm doing. There's a new one I just updated. Like, has it been updated in the past, like, 5 minutes? Oh, the update is signing. Thank you for confirming. Nero, are you like involved with the team or? No worries. I don't keep going through the website though, because I want to see how they're marketing it now. This just like you could mistake this for Arc here, which is hilarious. I get it. Like they should. There's such a huge opportunity making a well-maintained open source Arc alternative. I almost did it myself in Chrome. I'm just not going to build a freaking browser. Workspaces, compact mode, split views, very exciting. Sidebar, I'm not personally that into, but I can see the benefits. The glance, I turned off the glance feature in Arc. The customizability is one of my favorite aspects. Oh shit, somebody's in the chat who actually helps. Hard for us to do Mac. Legit, the main dev remote desktops into your MacBook that you got like 2 days ago. If one of the devs is committed, I would be down to put money towards getting them a Mac. Yeah, the new website is stunning. You guys killed it. Like this feels a lot less like a hobby project now. This feels like a legit competitor, which is funny because you're competing with a very well-funded business that just threw away the bag and you're going to win now. Like it's over. The sentiment war. I am very excited to do that video. Yes, Frost. Appreciate that. Let's actually hide it. And how do I apply that? I was going to wait for the new update to sign. What do I do in here? For which one? We possibly see it's still Firefox based, right? They didn't change that. I know that Chrome is the like name of the like window around the browser, but Chrome : // It's still Firefox. Okay, cool. The dev said, try right-clicking, change theme colors to gradients. Cool. I'm not going to do the CSS hack for now. I'm just going to wait for the update that fixes, or supposedly fixes this. Say potentially fixes this. Gonna marker and Zen for now. So I can do other things that I want to plan for content right now. I want to record at least 2 videos before I run off to play with my new toys. This was React Scan. I talk about it a bunch in the video. It's mostly the new iPad. Yeah, sure. Not sure when I'll get to reply because I'm like so busy. I also just remembered I haven't thanked any of the subs this stream, and there was a lot of people I missed. I'm going to go through all of you guys quick. Sorry. I was focused on an interview. Timo, starting us off strong. Appreciate that a ton. We got Renegade here, 21 months in straight, 23 months total. Almost at that 2-year mark. Scotty here with the Prime. Casey helped you win the Prime sub. I'll take it. Thank you so much to Casey for that. Got Insanity later, 30 months in, 32 total. Jesus Christ. CD Dev here, 30 months in as well. CD Villard, also here, 19 months. Jesus Christ. Ben Dev with the 7. Whole bunch of stream streaks from Turtles and Emily. Daniel here with the Prime. Thank you so much for that. Amon here with the 24 months. Appreciate each and every one of those. 28 total. Thank you for that. Frostjacked, always good to see you again. 8 months, tier 1. Thank you for that. We got Doc Devs. I almost mixed you up with Frosted Grandpa again. Trying to get better about that. We got Doc Dev here with the tier 3, 21 months in. Addy, always good to see you. Thank you again for all the help with reviews and whatnot. 24 months, Jesus. MJC here with the 22 months of Prime. Inuo Maduro with the raid. I wish I... Oh, I know who this was. This is the guy who was like roasting my video for a stream. I was actually really excited for that. I'm going to go back and watch it later. He was doing like his own take on my why there's no Laravel for JS thing. And I'm really excited to watch that later. Didn't know that was his handle. My bad. We got Polymathic with the 3 months. Thank you for that. Miko with the Prime. Thank you as well. Polymathic with the cheer. Pineapple Gong, 24 months, hitting that 2-year. So many people at the 2-year mark. Yash about to hit the 2-year mark. Mecco with the 5 gift subs. Thank you again, and as well for all the insights during the stream before. We were talking about all that. Ricky with the raid. Also, I missed Sve with the raid entirely. How'd I miss that? I suck. I am so sorry. How'd I totally miss this one? Well, if you like game dev stuff, go give Sve a follow because I screwed up with that one. We also got Snow Squire here with the 1-year mark. Congrats. All with the primes. You'd hit the button each time. Then Run Amok with the tier 1. Thank you so much for the support. Kevin, 24 months of tier 3, 31 total. Absolute legend. Thank you again. Run Amok with the 5 gift subs. Thanks again for all the support to all the gifters and everybody who was around for that. We got JBC Gannon here with the tier 1. Thank you so much for the new support. Dan Vale, 8 months in. Only giving you the up now. Oh, yeah, that was what we were just talking about. Thanks for that. We got Sifty here with the 7 months. Thank you for the support. Dark Axiom hitting that 1 year. And Rough Patch, 3 months in. If you have YouTube links for music, DM them to me. I will eventually listen. Good shit, Demon Wolf. If I'm not number 1, I can't even imagine how much Twitch you watch. I don't watch like anywhere near enough Twitch. I just watch YouTube. You can't 2x speed Twitch. Let's see if that update is ready. Not yet. Any update on when the update's ready? I'll probably just do that off stream, honestly, at this point. See if I can get it where I want it, and then do a video just glazing it. Oh, I did not see this. There's another. I like this. I like this a lot. That makes sense, George. Thank you. Gabriel, is there any other big news that I'm missing? Things I really should cover? OpenAuth. Oh, wrong button. AK plays 2 days ago. I feel like if I make a video about OpenAuth, it won't do as well as if I make a video about auth right now, because OpenAuth is absolutely part of the current auth story. I'm not going to do the quantum chip thing because I will sound way too stupid, and there's enough videos about it already. Like, I don't have enough insight there to do more than what a Fireship video would do, so I'm not going to. Cool. Wrong button. I did see this. I'm assuming Sora is also taken down by the chat. GPT being down. Yeah. Hard to cover when it's not up. Sora's not available in my country, except for the fact that I was using it yesterday. My country's the US. How am I supposed to make content if I don't have frickin' ChatGPT up to do it for me? Joking. ChatGPT barely affects my content beyond some... I know it really doesn't affect my content almost at all. There's no way anybody's going to watch a Dino 2.1 video. He'll barely watch my Dino 2.0 video. And I'm not that excited about Dino 2.1 either. It's like cool, but not enough for me to brand and package into a video. Especially like remember how insane our backlog of recorded videos is right now? Like I left these two spaces so we could stuff things in without upending the whole schedule. We have videos recorded and mostly done edited until January 16th right now. Yeah, the libsql Rust was tempting. I watched the Dia video. I hated it, and I don't want to do more videos where I'm just shitting on Browser Company. I did want to try Devin. Like, I was very tempted to give Devin a go, but I didn't set it up ahead of time. I have a person who works on it that was down to get me in early, so I might have to hit them up and do that. No, they have not rescheduled my call, and I'm at this point pretty certain they're not going to. Yeah, I at this point we should just do evergreens. Ooh, ice. This is actually what I really wanted to do. Let's do ice. Let's go in. God. Even if you don't use React, you've probably heard of Next.js and maybe even heard of Remix. Those are the two predominant frameworks for building with React. But what if I told you there's a third, that it's really popular, and you probably haven't heard of it? You might say I'm crazy, but have you? Have you heard of Ice before? This is a very fascinating project. Almost 20K stars on GitHub, a ton of really cool patterns, some unique ways of building. It really is a unique React framework that just so happens to be built by Alibaba in China. It is Alibaba that built it, right? Yes, cool. I'm excited to dive deep into this with y'all because there's some really cool stuff going on. But first, a word from today's sponsor. Cool. Credit where it's due. I found this because of Salty posting it on Twitter. There are some really cool things in there. The point that I realized I had to cover it was when they showed the syntax where they have their equivalent of views inline like directives for controlling things. Very interesting to see this in a React framework where you can say it should show this if is admin, otherwise this element shouldn't render. I now really want to understand how deep this goes. And the only way to do that is reading through the docs. First, want to see they do not have an English translation for the site, but I can make one. This is how every other dev that speaks any language other than English feels reading docs. ICE 3 is an application development framework that is based on React. An out-of-the-box R&D framework with built-in best practices such as project configuration, state management, data requests, permission management, allowing devs to focus more on business logic. Supports Web API, TypeScript, CSS modules, PostCSS. Application mode for SPA, server-side rendering, SSR, and static builds. Cool that it offers all of those. This really feels like Next in a lot of ways, but with a more in-your-face, like direct focus on mobile, because it's a much larger concern in these markets, especially mobile web. ICE is a front-end solution based on React. It provides basic capabilities like application construction, routing, debugging, and micro front-end stuff and integration capabilities based on the application development framework. Also combines visual operations, material reuse, and other solutions to lower the R&D threshold. Interesting. I've seen R&D a few times. I don't know if that's a bad translation. My assumption is that this is meant to make it easier to spin something up from scratch quickly. Why use ICE over Webpack directly? Webpack only provides the basic building capabilities. So this is very like reason of existing, similar to Next.js, where initially like setting up React with Webpack properly was annoying and Create React App didn't go far enough. Next was meant to go further and add server-side rendering for static generation. Now it is what it is today. ICE seems like it was going down a similar trajectory, but looks like they put their feet there, but it looks like they drew a line before going too far. Yeah. They do say that it's necessary to have some front-end experience. Good. Not pretending that you can just learn front-end using it. I have to see the directory structure. This is always something I'm curious about. Pages, about, layout. What does this do? Can I translate this here? God, I think I turned off the force click translate feature. Global layout components. Okay, so they have a global layout that you can put like this, similar to layouts in App Router, but the naming about TSX and home TSX suggests that it's not just like that they don't have a single page route. They do it this way instead. Pages, conventional routing, automatically generates routes based on the file. They have a whole section on routing. I am curious. Index about, repo preview. Interesting. I am curious what the mini program is, if that's like their like MPA path or something. Likely a bad translation. I'm amazed how much I can get out of this with just a Google Translate on the page, though. This is super cool. And outlets, interesting. They're taking parts from React Router and Remix as well as parts from Next.js here. Apparently their service mocking stuff is really cool. Y'all know how I feel about testing and mocking, but good they have it. This is also the only major front-end framework right now for React that takes micro front-end seriously. Next.js has historically tried to not care and avoid that stuff, and Remix doesn't either. Very interesting. Very interesting, the things that they have considered here. JSX Plus. Very scary, but I'm curious what they're doing with this. Although JSX has flexible syntax, a large number of curly braces plus JS syntax leads to decreasing in context switching and code readability. JSX Plus instructions solve the problem well. JSX is essentially a JS expression. The real DOM structure can only be calculated at runtime. JSX Plus introduces some static template features to meet compilation optimization. Interesting. And these JSX Plus extensions are things like the xif, xelse. Interesting. I don't love this because it's not nested. Like the direct relationship between the if and the else if is weird because I can't just move this element and have it work. I'm not as against like the x for or the x if, but once it's like x if then x else, that's when I get iffier about it. Ooh. X memo. That's actually really cool. You're saying that this can be cached and never rerun. Very interesting. slot scopes. Interesting. So the slot lets you say that this will get re-rendered out there separately. Very interesting. There's some cool stuff here. It's cool seeing a React framework being developed in a completely separate environment like this, where like they can see what we're doing and copy it, and then not copy things they don't like, and even do their own stuff too. I saw something similar in Vue. Was it Vue Vine? I'm almost certain that's right. Where somebody did the opposite, where they took some Reactisms and brought them to Vue. I want to find some examples in here. Vine lets you write syntax that looks a lot more similar to React, where you can have multiple functions that are components in the same file and have them call each other. You return using the Vine keyword with a template string. And in here, you can do the traditional Vue syntax, where you can have like an @click or a test ID or all the other props and directives you normally would have access to in Vue. But you can write your functions in a component within a function body like this, which I thought was really cool. This also, if I recall, is a project that largely started in China. And it's cool seeing these alternative approaches almost like unburdened by the current ecosystem and how strict that we are about things over here. It's so cool. The inclusion, again, like micro front ends. You know what? I think I might know who's sponsoring this video. I have a pending video with Zephyr Cloud, who is a company that focuses on making micro front ends viable for people. They're great. You can almost think of like Vercel, but for micro front ends. So if you're trying to do something with that type of architecture where you have hundreds upon hundreds of engineers with different opinions trying to ship at the same time, super cool. Yeah, I haven't seen a framework that actually took this seriously from the start. They have like framework config built in, a starting point for it. You can set a library name for your micro package or your micro front-end packages stuff and then mount it through their primitives. That is really cool. I might have to bug my friends over at Zephyr to ask them what they think about this, because they will likely know a lot more than me. I heard things about the mocking, so let's take a look at this quick too. So we mock and add JS or TS files. Mock user, get. Oh, interesting. So you actually put it out with like the mode and the path to mock things. That's really convenient, actually. That is actually really good. That's one of the most minimal solutions I've seen to mocking network dependencies. Actually, genuinely very clever. They're winning me over. Shall we try it? I have to. I'll put this in content. PM create ice. I don't want it in this directory. I think I have to give it a name like that. Weblight. It did put a git ignore, but it didn't get in it. Get in it. In it. Let's take a look. Package JSON, a great place to start. ICE runtime, React and React DOM are the only deps. And there's dev deps. TypeScript, good sign. Types for all these things. At ICE/app, I'm assuming that's how they bundle and do whatnot there. Very light on the deps. Am I going to be more scared after reading the PNPM lock? Yep. What does ICE runtime rely on? Just React. Interesting. I know this JSX runtime ICE shared and React router. So they are using React router under the hood. That's probably where the outlet stuff comes from. That makes sense. That makes a ton of sense. Did these guys beat Remix to static rendering? Because that'd be really funny if they did. What's document TSX? This is the document. Use workspace version. Will that shut that up? No. Why does it not know that? Interesting. It should know what ICE is from all the things installed, but maybe because it's not the named module, it's upset. I'll ignore that part for now. It's a small detail. I did not know there's an ESLint rule to let you know that your identifiers are too short. I might turn that on. I hate single letter variables so much. Sorry, Mark. He'll literally quit if I turn that on. JSON, seeing what the, start is what we would want then. Cool. ICE. Let's try editing some stuff here. Hello, nerds. Please sub. Hot reloading's working. Doesn't break the state. All good signs so far. I don't know why ESLint's now being mad about things like that in single quotes. I shouldn't be as annoyed by these things as I am, but the fact that your own ESLint rules aren't being followed by your own template always pisses me off, because then I feel like I have to do, like, I'm assuming they have an ESLint fix and a stylint fix. So if I like PNPM run ESLint fix or on stylint fix, if this changed anything in the code, which it did, that to me is a concern, because that means they're not even following these rules as they're prescribing them to me. It's a small thing, but it's a thing nonetheless. Interesting. Let's make a new route. Test route.tsx. I'm going to not include any of these things. Let's just div sup nerds. This is test route. No, does it have to be a folder? Oh, I'm not running the dev server. I'm stupid. Ignore me. I'm going to delete this and see if it still works. It does. Cool. Yeah. Turns out running the dev server helps when you're doing things that rely on the dev server. All the parts are here. This is like a legit framework. I mean, I would hope so. It has 20K stars. But like, this is cool. I'm giving it a star for sure. I want to see what their state recommendations are because they mentioned that. State. Oh, Redux. Okay, at least they have Immer. Immer makes Redux significantly less painful. I think it's basically enforced if you're using something like Redux Toolkit, which they aren't. Interesting. Ice store. Let's translate this page. Does it not even give me an option to translate the page? Can I tell Arc to translate the page anyways? Okay, what happened to Google Auto Translate? I'm opening these in Chrome because it more reliably offers me translate. Oh, right click the page, translate. Okay, there we go. Translate page to English. Haha. So I can go back here and do the same? I can. iStore simple friendly management solution or state management solution for React apps. Has following core features: simple familiar API, integrated async processing, very interesting. Support components with or class components still, so you can use it with old projects, and TypeScript support. Interesting. This looks very similar to the XState store thing they recently put out. That's like the minimal alternative to Zustand. Very similar. Interesting. Oh shit, Diego got a shout out. Diego's a legend. And his work on Constate, which was a better set of wrappers around context stuff for state, if I recall, was an inspiration for them. Really dope they shouted that out. These guys get it. I wouldn't be surprised if a handful of the people working on ICE watch my videos and are going to get really hyped when this happens. And respect to them. They're living in their own world and building genuinely really cool stuff in it. What else do we have here? They have a whole doc page on element visibility. Use visibility change component to monitor when a specified element is currently visible or not. ICE appear. Interesting. I want a npm org at ICE. How easily can I find this? I want the org. Can you look at all the things an org did on npm.js? Okay, cool. Here we are. ICE app, ICE appear, ICE bundles, ICE cache canvas, supporting canvas. Interesting. ICE CLI, shared create app stuff, CSS module stuff, a ton of it. ICE form, ICE hook store, their own JSX runtime. There is so much stuff here. This is like a whole world I've just never gotten to dig into. Even like their own stuff building around Docusaurus. It's like I feel like I'm peering into a whole different world that is like speaking my language but isn't at the same time. This is so cool. Yeah, these guys are absolutely shipping 113 packages, and I had heard of none of them before. Somebody called it they've never seen anyone use unstable activity from React before. I also haven't. Yeah, they're heavily using all the off-screen stuff. Yeah, this is the rename of unstable off-screen to unstable activity. Look at like half the results for unstable activity are in Chinese because it's only like major recommendation for use is in ICE. That's actually really cool. Good for them. This is their React query clone. It actually looks quite different and much more focused on URLs. So they have their own request function. Await request, URL, status, await request, common usage, request get user, request post. You can have a config for them too by passing it like that. That's actually really cool. Use request based on A hooks. Use request. There's so many shout outs to the other things that they're relying on and inspired by too. That's a problem I've seen in a lot of open source stuff where they don't do it. This is just really good open source. Like they're doing everything right. They're shouting everything out. They are documenting the hell out of the stuff they're doing. Alibaba's killing it. Credit where it's due. This is way better than I would have expected. Like I've seen like a dozen React frameworks that aren't Next or Remix. I would put this at a similar level of flushed out. This is really good. Having all of these options with use request, it's React query, but just to use like their request handling that they already had built. Does it not request by default? You have to tell it to. That is interesting. That is a very different workflow than I would expect. Actual business is more likely to be triggered manually. Interesting. So their use of this is primarily for like users doing things. So they don't want to default fetch it. Very interesting. Very, very different from the defaults of like React Query, for example, which is much more aggressively assuming you're using it to fetch data. Huh. I want to try the SSG stuff. You have to use data. Does it do static building by default? You don't have to config that? PM run build. build. Yeah, look at that. We have an index HTML. Hello nerds, please sub has the default stuff there. And then the test route, which has our minimal. I'll save it so it's formatted better. Has our minimal little sup nerds. Look at that. Damn. That puts it ahead of Remix. This is actually really cool. First, I want to see, like, does this opt out if you get data? No, it doesn't. So in order to opt out of SSG, you have to specify you want SSR true in your config. When SSR is enabled, the method exporter and the routing component data loader will be executed on the server first. The SSR rendering is successful. It won't be called again on the client-side data loader, but the SSR result will be reused. It's only called on the client side when the page is redirected through routing on the browser side or the page is downgraded data loader. Okay, so you have to do a manual revalidation on the client side in order to get updated data. Makes sense. I guess the thing that isn't clear is, can you do SSR and SSG? Can I have some routes SSR and some routes not? You can ignore and exclude certain files in the SSG config. Okay. In here. Oh, here you go. You can use the ignore parameter to filter specific files for SSR or SSG products. Cool. Good shit. This is so flushed out. This is so far along. It's almost like they've been working on this for years. Actually, though, this is dope. Code splitting built in. Ability to manually enable or disable syntax feature. The TypeScript checker is part of your build. Disabled by default because it shouldn't be part of your build. You should run it separately. Thank you. Just good decisions all around. Also, to go back to the data loading thing with their data hook for the request thing, by making the default be you have to run that function, they've basically brute forced you to use a better data loading pattern, or at the very least make you feel bad for calling request inline like that. They show the conventional, God, I'm sure all of you have written this code. Please, if your way of getting data in React looks like this, watch my React query videos. Please, please. But they have to use data and the data loader. Yeah, they're really trying to push you in that direction. Makes a ton of sense. You can even defer it with a defer helper. This is really good. Yeah, I have no notes. I'm excited to see how they support server components, because that's like the only thing I haven't seen yet. Doesn't come up in search because it's still a new thing. Yeah. Yeah. Await. Did they have an await block? Yeah. This is another remixy thing where you could have an await block that you pass a promise that comes from the server. So here we have use info is await and item info is await. And we have these two promises coming from the data loader. And these are promises. And since they're using the data loading stuff built into React Router and Remix here, they might have rolled their own. I'm almost positive that's what they're using under the hood because they are using React Router under the hood. Now these promises get serialized to the client, and you can await them with their await helper component, and then it's a higher order component. So it just calls the child with whatever the response from this promise is. So you don't have to block on the server to get the user back a response. This is a really powerful pattern. Yeah, this is one of the most flushed out ways to use React Router that I've ever seen. This is great. Historically, I know Vue has had a much stronger hold in Chinese markets because their documentation and resources and everything have been much, much further along in terms of their internationalization. One of the things I'm most impressed with here is that the framework understands that most like non-English speakers are going to struggle a lot with these things in React, because even the ones who do speak English and read the docs struggle with a lot of these things. So they have found a balance of documentation to lead you down the right path, as well as good defaults and patterns to make you less likely to fall down the wrong path to set people up for success in React. That's awesome. This is really good stuff. And I honestly think we can learn a lot in the Western framework world about what went well here. I would love to chat with some people who use ICE full time. If that's you, let me know in the comments or use the email that's on my YouTube channel, because this is genuinely really cool and I want to keep exploring. I don't want my bias of being a native English speaker in the West to prevent me from seeing these awesome innovations. So feel free to hit me up when you find things like this, and please contact me if you're working in this framework every day. I genuinely want to know more. I got nothing else for now, so until next time, peace, nerds. Cool. That's going to be a fun one. I'm actually really excited. I wouldn't buy any KVM that isn't level 1 tech. I don't know how cheap their single monitor ones are going to be. Like, if I was buying a KVM, I would want it to be super reliable, and I'm going to spend the money on one of theirs. But they are not cheap. What I do now is I get monitors where they have a port, like they have a display port and a Thunderbolt, because my use for this is I have a laptop that I want to plug into the monitor and a desktop that's otherwise plugged in. And now I can one button switch inputs on the monitor, and it switches everything else over because I have all the USB and shit plugged into the monitor. So nice monitors now offer this, which is cool. I hate using the USB on my monitor, but for this particular use case, it's okay. Apparently, Zen fixed my bug, so I'll marker more for Zen, maybe. Apparently, Zen fixed my bug. Let's see. About. Applying update. Tabs on the right. No. I was excited. Rip. I'm not doing the CSS thing. Guy you're making for me, you'll have it fixed out? Okay, cool. Neuro, I give you permission to ping me in that Discord, in the Zen one. When that happens, I do really want to give this a shot and do it right. And don't use that. Cool. Is it still? this I can archive now because we basically did this. To stream. Dead. That feels good. That one's been in here forever. Yeah, these are all things I want to film eventually. I don't know if I have it in me right now. I'm a little drained. I want to do the itch.io thing. Yeah, let's do that. Label priority. Close, 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 close. This will be the last one for the day, I think. If you're a prolific enough gamer, you might have noticed that itch.io was down a few days ago. The reason is utter chaos. Throughout my years, I've seen a lot of different ways that a website can go down. I've never seen one quite as weird, dumb, and just worth talking about as this one. Quickly, from their words, itch.io has been taken down by Original Funko because they used some trash AI-powered brand protection software that created some bogus phishing report to our registrar, who ignored our responses and just disabled the domain. This isn't that simple. This is hilarious. They even called his mom. Yes, the itch.io founder and owner's mom got called because they were so upset about the social media. This is chaos, and we have a lot to talk about. And I promise you, we'll get there right after a quick word from today's sponsor. Oh boy, oh boy. Thankfully, by the time you're watching this video, itch.io is again back online, which is very good. The indie game scene needs itch. If it fails, a lot of indie game dev goes along with it. We need itch.io to survive. These types of things are, to be frank, pathetic. Also, credit to Pirate Software for putting this on my radar. Absolute chaos. We need to break this down layer by layer. Obviously, the immediate effect, itch.io was taken down. The takedown happened because of I Want My Name, which is a DNS provider. I have to Excalibur this because there's a lot of layers, and I want to make sure that we get it right. So, if you know anything about software, you know it is built on layers. If you have something like a DNS provider, this has to be built on something. This is built on registrars and ICANN standards shit. So on top of the registrars, we have a DNS provider. The DNS provider is something that you now use as the service owner. So when you are the owner of something like ping.gg, itch.io, whatever, you have built on top of the DNS provider by buying the domain through them, they are buying things through the registrar. In this case, the service is a shop for buying games. So this service has a layer on top, which is users distributing software. So now if you're a game dev, you're shipping things on itch.io. So I should label these all. itch.io is this layer. You have a game dev that is this layer. We have I want my name is the DNS layer. And then you have a whole different layer, which is users buying the software. This is the layer I don't want to talk about, the gamer. What's interesting when you're in scenarios like this is how the liability chain works. Let's say you're a separate party, in this case, Funko. And you have identified that somebody is distributing software that violates your trademark. You are Funko, and you've identified that at this layer, a game dev is doing something that is illegal. In an ideal world, Funko would go straight to that game dev doing that and tell them, hey, if you don't stop, we're going to go after you. Because this isn't itch.io violating anything. This certainly isn't I want my name violating anything. This is a game dev supposedly using Funko stuff in an unlicensed way that Funko is now going after them for. But Funko didn't do that. You'd think, okay, the next best thing, they're going to go to itch. Nope. Because Funko's not the one doing it. Funny enough, what happened here is there's a middleman. So Funko exists over here. Now there is this, what's the name of the service? I think it's Brand Shield. You have this wonderful Brand Shield service. Did I get that right? Yes, Brand Shield. Funko contracts to Brand Shield to protect their brand. And Brand Shield has their special way of doing this. Brand Shield decided that it's easier to not go to the game dev who's causing the problem, certainly not to go to the service owner, but instead shortcutting all the way to the DNS provider, and also in that process threatening them, saying, hey, by the way, if you don't comply with our demands, we're going to go to the registrars that you work with and tell them, by the way, you shouldn't work with this company. They're distributing things that are illegal. And this is where the problem happens. The thing that sucks here is a user on this layer, somebody who is distributing things on your service, is capable of causing something much lower in your chain, in this case, your DNS. Without you being involved at all, it's possible for somebody distributing software on your service to cause the things you're building on top of to get fucky. To give an example for us, because I dealt with this recently with Upload Thing. By the way, if you're not familiar, we built the best way to manage file uploads in your full stack applications. Upload Thing allows users to upload files. We had a similar problem. Instead of registrars, I'll put ISPs on the bottom, so internet service providers. Then we have our hosting providers. In this case, it's Cloudflare. Then we have service owner, that's us, Upload Thing. User, or I'll say service customers, which in this case would be a full stack dev. And you have web app users. I'll say this is users of service, or users of, or I don't even know what to call this. Actual end user. Cool. So it's fun here now. Let's say somebody builds a clone of Google Drive using Upload Thing. If you built an Upload Thing clone for Google Drive, now you have users. Let's say one of those users uploads spyware. Now we have hosted on UTF-SIO /f/spyware.exe. some end user uploads this file. Now this file exists on Cloudflare's infrastructure. This is key, and this is really dangerous, not because like this domain is associated with Cloudflare, but because this file is being served from one of their IP addresses. So because a user all the way up the stack here has uploaded some spyware, this isn't the full stack devs problem. This isn't even our problem with upload thing. This becomes Cloudflare's problem because an ISP now will hit up Cloudflare and say, hey, we're going to block your IP addresses because they're being used to serve malware. And then we get a scary letter from Cloudflare saying, hey, upload thing builders, there is spyware being served from your service. You need to get rid of this ASAP. Because if we don't, then Cloudflare's IP addresses get blocked by ISPs. Now we have to go up the chain yet again. So Cloudflare goes to us and says, hey, what the fuck, fix this. Now we have to go up the chain once more and say, hey, we just deleted this file, fuck you. Our options now are we can ban this user if we think they are aware of the malicious actions and not doing anything, or they themselves are the malicious actor. Or they now have to go up and they come back to us and say, no, that wasn't us. We had a malicious user. We're sorry. We'll do better filtering for it. And they have to go ban their individual user. So somebody all the way up the chain as a bad actor here can result in an ISP banning Cloudflare's IP addresses. That's why these chains suck and why they have to be addressed as aggressively as they do. But ideally, this would have happened much higher up the chain, which is something we're now working on. We're going to be restricting your ability to host files that are runnable and executable. You won't be able to host bash scripts or CMD files or EXEs on free tiers ever again. That's over now. We've learned our lesson. In the future, we'll be doing more scanning and things like that as well, working on introducing all of that. The fact that these things affect us in these hierarchies sucks because now a user of a customer of our service can cause Cloudflare problems. Thankfully, this was a notification system where we were told this was happening, where in this case, Brand Shield didn't give anyone any opportunity here. They went to I Want My Name and said, if you don't ban this DNS and ban this domain right now, we are no longer going to allow you to work with ISPs. We will force legal action. We will go to these ISPs. You're screwed. Get rid of this domain. And out of panic, and also I would argue incompetence, I Want My Name caved and removed one of the most popular domains on the internet, one of the most popular IO domains for sure, because they suck at their jobs. But so does Brand Shield, because Brand Shield should have had any system to notice, oh, itch.io is a service for distributing other people's software. They are the ones we should be hitting up. But they didn't do that. They went straight to I Want My Name and got itch.io banned from the internet for like over 24 hours. And here's what Brand Shield had to say. You might notice they have replies off and also a lot of community notes on this. We want to address recent reports surrounding a website takedown. Brand Shield serves as a trusted partner to many brands. Our AI-driven platform detects potential threats and provides analysis. And in this case, an abuse was identified from an itch.io subdomain. We identified and reported the infringement and requested a takedown of the URL in question, not of the entire itch.io domain. Temporary takedown of the website was a decision made by the service providers, not Brand Shield, because you didn't report it to the right provider. You reported it to the DNS provider, not to itch.io. Brand Shield remains committed to supporting our clients by identifying potential digital threats and infringements. We encourage platforms to implement stronger self-regulation systems that prevent such issues from escalating. Nonsense. Brand Shield needs to realize that a subdomain is probably owned by the original domain, and they should probably go to the service provider of the original domain to figure out what is wrong there. And calling itch.io's mom, like that is horrifying. Like, I get that you want to get some press stuff and you want to like cool it down. And the itch.io guy probably wasn't responding to your bullshit Funko Pop requests, but going after his mom is just insane. I would have loved to just blame Brand Shield and say Funko Pop's not the problem, but this alone means all of these companies fucking suck and should be mocked relentlessly for what they've done. Yeah. They also moved off of I want my name after this because what the fuck? Yeah. Here's what Pirate had to say. Instead of filing a DMCA claim to itch.io, you sent a takedown request to their registrar. Are you incompetent or are you just lying about your intentions? For those that don't understand why this would set me off, the company Brand Shield is a brand protection company that files infringement claims on behalf of their customers. In this case, they filed an infringement request with Itch's registrar for a user-generated page that contained Funko Pop branding. This led to a complete takedown of the website for the better half of this morning. Sorry, I thought it was a whole day. It was only half a day, I guess. This is the equivalent to Twitch being taken down because a single user was streaming a copyrighted movie. Yep, exactly. And a good link from, funny enough, Twitch staff. itch.io's terms of service. Look at that. They have a whole section here for the DMCA. If you believe one of our publishers has violated your copyright, please let us know about your complaint with the required information so we can address the complaint. If you think a complaint was filed in error, you can also contact us to address your concerns. There you go. Technically speaking, since neither Brand Shield nor Funko are customers of itch.io, they're not expected to comply with itch.io's terms, but you should check them quick to figure out what the right method is for reporting. But since this isn't a human doing a correct method of reporting, this is a crappy rogue AI tool sending threatening emails around. Disgusting. This is what happens when you let AI go without a human in the middle. Absolute fundamental failure. And Brand Shield should at the very least check how popular a domain is before sending one of these bullshit accusations. Ideally, they would shut down because this is bullshit. But like, yeah, God. Yeah. As Pirate said, Itch has a very easy process for handling DMCA claims, and these processes were ignored. It's clear that Brand Shield didn't do any research before firing the gun, and they shouldn't be taking actions as such. Brand protection companies should know better. The registrar should know better, and Funko Pop should know better. To follow this up, Brand Shield has tried to blame the victim here. Yes. They are continuing to try and blame people for doing things right effectively. It's kind of insane. It's like this should be the end of their business. And I would be genuinely somewhat disappointed if people continue to sign up for their service after this. Because I'd hope when you Google search them, this comes up first. God. That's all I got on this one. Don't break copyright laws. And if you do, or you see someone doing it, report it the right way, please. Until next time, peace, nerds. Cool. One more down. Oh, Funko had a response. Cool. Sneak this in, phase wherever it fits. At Funko, we hold a deep respect and appreciation for indie games, indie gamers, and indie devs. We're fans of fans, and we love the creativity and passion that define the gaming community. Recently, one of our brand protection partners identified a page on Itch imitating the Funko Fusion development website. A takedown request was issued to address a specific page. Funko did not request a takedown of the Itch platform, and we're happy to see the sites back up this morning. We reached out to them to engage with them on this issue, and we deeply appreciate the understanding of the gaming community as the details are determined. Yeah, as the top reply says, it's a lot of words to not say that they're sorry. And on top of that, not admitting that their brand partner, Brand Shield, didn't contact Itch. They skipped multiple steps and went all the way down the chain. That, I would argue, there could be a lawsuit here for irresponsible behavior on a brand with intention to damage. It's pretty absurd. Yeah, this also should have been a DMCA request. If it was actually phishing, like they were trying to look like Funko Fusion when they weren't, a fraud and phishing report might make sense, But again, that should go to itch.io, not to their registrar. And I can't give any benefit of the doubt to Funko over any of these steps because of how they've behaved. Yeah, FaZe, sneak that in wherever it fits. You can find a spot. Cool. That was a fun one. It is almost 7 o'clock. I've been going for almost 6 hours. We got 2 actual videos and the collab, which is it's a video. Not sure when it will come out, but it's done. My stream later this week. I can't tomorrow. I have a bunch of meetings. I might stream Friday or Saturday to gun out more things. If there's some big news drop or I can finally use Sora and make a video about it, I'll probably go live. I've had my fun. I'm going to go get these assets uploaded and play with my toys. Let's figure out who we're raiding. Oh, look, Ludwig streaming on Twitch again. We haven't given Acorn a raid for a bit. How long has she been up for? Oh, yeah, this new Twitch player is garbage. I see how people are mad. 3 hours. Hopefully she'll be going for a bit longer. Have fun. Goodbye, nerds. See you Friday, Saturday, or worst case, Wednesday. I don't think I have anything that's coming Wednesday. There's some Wednesday where I have to cancel in the near future. I don't know which one. Make sure it's not this one quick. No, I'm good for this coming Wednesday. I don't know when the Wednesday I'm worried about is. Is it Christmas? Oh, yeah, Christmas Day is Wednesday. That's what it is. Cool. Have fun with Acorn. Goodbye. Farewell. Thank you all. And goodbye to YouTube as well.